Good morning, in particular to our friend Vicentiu. And I don't apologize for my English. My English is quite bad, but I do not apologize because, for instance, it's as like in the barbaric peoples do not apologize to the Roman because they don't speak quite well Latin. I have the same situation. I dislike to say mistakes in French or in Spanish or other languages, but in English I think I am obliged to speak English since I speak English as it comes out. Okay. Bene. Allora, the first speaker is Professor Galdi. Here I see Professor Coffee Break, but no Galdi. And the title is Hopf, Bifurcation and Resonance in a Fluid Structure Problem. Please, Professor Galdi.
No, I already have
You
mine.
have it?
Yes.
Oh, okay.
Thank you. Okay, perfect. Okay, so good morning, everyone. Thanks for being here. And first of all, happy birthday, Professor Radulescu. We met basically only twice. That's the second time I have the pleasure of seeing you. And the other time was when we had a conference in honor of Professor Daviga's 16th birthday, right? 16, when you were 16 years old. Yes, so,
10 years ago.
right. And of course, I would like to thank the scientific committee for having me here, Professor Cassani, Professor Pucci, and Professor Daviga. And so, that's the title of my talk. So this is part of research that involves Professor Bonheur from the Free University of Brussels, and Professor Filippo Gazzola from the Politecnico, sponsored by National Science Foundation. This is publicity, I have to say that, because I'm paid for that. And you know, the whole research will appear on the memoirs of the American Mathematical Society. So, motivation. So the motivation is very simple to explain. So we know from daily life experience that if you have a fluid that moves around the structure, then eventually the structure will oscillate. And a typical example are musical instruments like clarinet, saxophone, oboe, everything. A more sophisticated example is the aeolian harp, that basically is a frame, a wooden frame of strings, and as soon as the wind goes through the string starts oscillating and producing a beautiful sound. However, I'm not focusing on musical instruments or aeolian harp. My point is suspension bridges that I've learned from Professor Gazzola. So he has a lot of interesting work on suspension bridges, and there are many, many interesting mathematical aspects that, and you know, I will describe one of them. So suspension bridges, so what is a suspension bridge? As the word say, is a bridge that is suspended, right? So basically there are cables here. There are cables that go, there are two cables in this case that hold the deck of the bridge. These are kind of horizontal. In fact, this is a catenary. And there are other cables, vertical cables, that you know, hold the deck in place. So there is no structure under the bridge. This Ponte des Invalides is the first, actually, the first suspension bridge that was constructed in Europe and is in Paris. And the interesting notice about this bridge is that this was built by our friend Navier, so the French engineer, the Navier-Stokes. So, and the more interesting thing is that this bridge basically was never used, because a few days before the inauguration, the bridge cracked. And yes, the buttresses here and here showed cracks, and therefore was never, so this was the first blow up of Navier-Stokes. In fact, the bridge was basically dismantled, and they constructed another bridge. And in fact, now the current Pont des Invalides, the bridge is not a suspension bridge, but it's a regular bridge with arches and everything. So, but the interesting notice is that, you know, Navier was the first about So this is a more modern bridge, and this is the longest bridge, and is in Çanakkale in Turkey, and the span of the bridge is over 1 kilometer. So this is for over 1 kilometer. This is only held by cables. Now, what is the interesting part, so to speak, interesting part of concerning these bridges, is that when the wind hits the bridges, they start oscillating, okay? And the outcome of this oscillation can be really catastrophic, like the famous Tacoma Narrows Bridge in the United States that collapsed and eventually fell completely. And so let's try to understand what is the cause of the oscillation from the first from the physical viewpoint, and then a mathematical model for it. So let's say that lambda is a measure of the wind intensity, so to speak. So how much this wind blows. And so we have this situation here. There is a kind of critical number of the intensity of the wind, let's say, that as long as the intensity is less than this lambda c, the bridge is in a stable equilibrium, and the motion of the fluid, of the air, is steady. As soon as this lambda increases above this critical value, then the airflow becomes oscillatory. So it's no longer steady, oscillatory, due to vortex shedding. And the frequency of this oscillation is such that makes the bridge oscillate with the same frequency. And this is from the mathematical viewpoint. This is a classical Hopf bifurcation going from a steady state to a time periodic state. Now, as soon as one observes that the frequency of the oscillation increases with the intensity of the wind, and eventually will hit one of the natural frequencies of the bridge, right? Because this bridge is an elastic structure. And so when this F hits one of the natural frequencies, what happens is that this F synchronizes with Fn. So in other words, you increase the wind intensity, but the frequency stays locked in with the natural frequency of the bridge. And this provokes disruptive resonance, and eventually the bridge will collapse. So now, engineers attribute this phenomenon to Hopf bifurcation. So my point is just to analyze this relation between Hopf bifurcation and resonance. And we will see that basically, unlike what engineers predict, so this is one win of mathematicians, is that Hopf bifurcation cannot be considered as responsible for this disaster. Okay? That's what I would like to show you. Now, the model. As a model, I use what engineers use. So it's not, this is not the classical model made by mathematicians. This is made by engineers. Blackburn and Henderson, for instance, or Malika Chomans in 2011. So here is a very simple picture, a sketch of the model. Basically, there is a structure. This is not the bridge. This is a cross-section of the bridge. So the bridge comes out of the screen, right? So this is a cross-section, and that is held in place by elastic forces, okay? So this is the wind that hits the structure along a given direction, E1, for instance. And then due to once this intensity overcomes the critical value, the bridge will start oscillating. So that's the typical model that engineers use. Now, mathematically, the structure, so the cross-section of the bridge, is viewed as a rigid body, so a compact smooth set of R3, smooth C2, for instance, but we can go down to Lipschitz eventually, subjected to a linear restoring force. So this is the elastic force that, as you see, may be anisotropic. So here, instead of having the classical, what we teach in Calculus 1, minus lambda minus L delta, this is a matrix that is symmetric, positive, definite, and so this is what we assume, anisotropy possibly of the elastic force. Physically, I put it in brackets because it's not relevant, but I mean, we are assuming that this bridge can go up and down, left and right, sideways, but cannot turn. So physically, we have to apply a torque that prevents from rotation, okay? As far as the fluid we assume that is a Navier-Stokes that fills the whole space outside the structure, okay? Now you may say air, Navier-Stokes. Yes, air can be modeled as Navier-Stokes because the compressibility of air is very, very, very small. Try to blow in a bottle and see if, how small the compressibility of the air is. In any case, this is a model by engineers. So now, equations. These are the Navier-Stokes equations, suitably modified because it's, of course, it's a fluid structure problem. So here, there is the velocity here, delta dot, the velocity of the structure that comes into the Navier-Stokes equations. Velocity at infinity of the velocity field of the fluid is assumed to be 0 after a change of variables. And so this is basically modified Navier-Stokes equations. This is the equation of the structure that you see is a non-local equation. And without this term is just the typical oscillation of the harmonic oscillator, delta double dot plus A delta equals 0. So the meaning of this force here, so it's Newton's law basically, the meaning of this term here is the force, and this will be extremely important for our analysis. This is the force exerted by the fluid on the structure, okay? So, and concerning the other symbols, omega is the exterior of the body, so where the fluid lives. Lambda is the intensity, which is a Reynolds number, so involves the velocity of the wind, let's say, the diameter of the body and the viscosity of the liquid. And this m appearing here is the ratio between the mass of the displaced liquid, rho is the density of the fluid, and the mass of the structure. So we would like to study this problem from the mathematical viewpoint. Now, a few comments. So the first thing is that there is one data. The problem has one data, is the direction of the wind. And it's constant, okay? It's constant because it's just the unit vector. The unknowns are velocity of the fluid, pressure of the fluid, and the displacement of the structure. Notice that this problem on purpose is only partially dissipated. So there is dissipation in the Navier-Stokes equations, but there is no dissipation in the structure. So this is really the best way of, as we know from calculus 1, calculus 2, of studying forced oscillations, where there is no damping that could prevent resonance. So it's done on purpose. So the system has no dissipation in the structure. Okay, so now what you can show, and I just state the theorem without giving any details because it's not what I'm interested in. You can show that for any lambda, so whatever is the intensity of the wind, you can always find the corresponding steady state equilibrium solution, always. Okay, so the steady state exists for any intensity of the wind. However, stability, and it's another story. So concerning the uniqueness and stability of this steady configuration, it only holds if lambda is less than some lambda c. That depends on physical parameters, all the physical parameters. So the body, the restoring force, and the ratio of the masses. And so if lambda is less than lambda c, the steady flow is unique and stable. And more importantly, there are no oscillatory solutions. Okay, so you have only the steady state equilibrium situation. Now, let's go to the more interesting part, the oscillatory regime. So the oscillatory regime, so we are expecting that it must come through an Hopf-like bifurcation, because there is no time periodic driving mechanism. The only mechanism, as I said, the driving force is only a unit vector in the direction you want. So time periodic solutions can only take place via Hopf-like bifurcation. Now, this is the point. Hopf bifurcation is viewed by engineers as the main cause of resonance and possibly collapse of the structure for the reason that I just explained at the beginning. Now, what is the explanation? So the engineers look at the, this is not, okay. So anyways, the engineers, okay, here we go. Look at the resonance problem as a forced oscillation. So this is the force, as I said, exerted by the fluid on the structure so that when the fluid is in the oscillatory regime, this force is of course time periodic. So it's a classical problem that we teach in undergraduate classes of forced oscillations, right? So if we want to solve this problem, when f is prescribed, then we expand both delta and f in Fourier series, and we come up with this equation for the component of the Fourier expansion, right? And so if mu sub I are the eigenvalues of the matrix A, and it happens that omega squared is equal to this quantity here, so there is a kappa hat such that for this kappa hat, omega squared is exactly mu I kappa hat minus 2, then basically this problem cannot be inverted in terms of delta, right? We cannot solve for delta unless the corresponding f is restricted, and what we get, that periodicity is lost, and the corresponding solution to the problem goes to infinity. And so this is the way in which the engineers explain the occurrence of resonance in bridges. Basically, this is the bottom line. A little bit more sophisticated, but this is the main idea. So you see, this is the resonance condition. And so this argument also tells us that occurrence of resonance prevents the existence of time periodic solution with arbitrary omega, because if omega is like that, so omega is the square root of this, then a time periodic solution doesn't exist. So there is a restriction on the size or on the value of the period, okay? And so now we can show that Hopf bifurcation does not require any restriction. So Hopf bifurcation can happen at any frequency, okay? Now, the leading idea, in fact, you know, of course, the paper is technical, so I'm not going to do anything like that. Who is interested could, I can give details. But let me tell you the main idea of the whole thing. So this is the force that is exerted by the fluid on the structure, right? Now, this force has two components in principle. So there is, of course, a time periodicity aspect of this force that leads to resonance, as we said before. However, this has also a damping effect here. You know, as we know very well, if we try to move something in a fluid, there is some resistance, right? So here, in this integral here, this non-local quantity, there are two aspects. The time periodicity, yes, that may lead to resonance, but there is also a damping effect. And so if the damping effect prevails on the time periodicity, let's say, so 2 prevails on 1, then resonance might not take place. Because as soon as basically the bridge, let's say, starts oscillating, it is damped by the viscosity of the fluid, right? So the whole thing is to show, for this presentation, or at least to investigate whether, which is more important between the two. Is 2 more important than 1, or is 1 more important than 2? Okay, so now let's formulate the bifurcation problem in more specific terms. So we have a smooth family of equilibria. Here, again, this doesn't work. So this is a smooth family of equilibria, and we are interested for the Reynolds number in a neighborhood of some lambda naught, where we are looking for this bifurcation. And so the classical way of looking at bifurcation from a steady state is just to look for solutions that are steady state plus some time periodic perturbation, right? So if we write the equations for the time periodic perturbation and we introduce these symbols, basically think of L as the linear part of the equation and N as the nonlinear part, then for the perturbation U, P, and delta, you get this set of equations, okay, where basically, there is no longer E1, so the data has disappeared. And the bifurcation problem consists in finding a non-trivial family of time periodic solutions depending on lambda in the neighborhood of lambda naught, and such that when lambda goes to lambda naught, U, P, and delta go to the identically zero solution. Because remember, these are perturbations of the steady state. Okay, so now, Here, there is the interesting mathematical part, but as I said, the technicality, I'm not interested in the technicality. I just want to show you what is the main idea why there is no resonance, okay? So, but the challenging, interesting part of the question is that the classical theory of bifurcation does not apply in this case. And what is the reason? The reason is that 0 is in the essential spectrum of the linear operator. So here, if we were not dealing with Navier-Stokes, we would just add a little term to the Navier-Stokes equations and take this 0 out of the essential spectrum. But this will be cheating. So we have to deal with the fact that 0 is in the essential spectrum. And so I wrote a couple of papers about this type of problems in 15 and 16, where I introduce a general bifurcation theory that also applies for time periodic solutions, that also applies when 0 is in the essential spectrum. Okay, so bifurcation can happen also from when 0 is not an eigenvalue, basically. Now, let me tell you again the main steps, but I will emphasize only the step that is relevant to this talk. So the steps are, first of all, I change the classical scale of time. So we introduce this time tau in such a way that the t periodicity goes in 2 pi periodicity. This is a famous trick that goes back to Poincaré, so nothing there. Then one split the unknowns into an average with a bar and an oscillatory component. So this component, the W, P, and Xi, have 0 average in time. Okay, so they are really oscillatory. Okay, because the non-oscillatory part is englobed in the averages. Now, once we do the splitting, the original problem splits into a nonlinear coupled elliptic parabolic system in these unknowns. So the average for an elliptic problem and the W, P, and Xi parabolic oscillatory problem, purely oscillatory because the average is 0. And the main trick here is to study these two problems in different functional framework. So without, as I said, this is the technical part that I'm not interested in, but the trick is that you study the two problems, unlike the classical Hopf bifurcation approach, you study the two problems for the average and the oscillatory in two different functional frameworks. And in this case, the problem of 0 being in the essential spectrum doesn't play any role at all, because okay, without going into details, who's interested, I can give details. Okay, so besides some other technical request, the crucial point of this approach is that you take the equation for the purely oscillatory component and linearize completely this problem, okay? You take just the simplest linearization of the problem, and you have to show that the solution to this linearized problem, which I call FLP, fully linearized problem, must have one and only one solution in a maximal regularity class, in the L2 maximal regularity class. So let me tell you what is this in our case. So this fundamental linearized problem goes as follows. So you take a 2 periodic force, F, with values in R3, so it's just a vector function, okay, with 0 average, so purely oscillatory. Omega is given, lambda is given, and you have to find a unique 2 pi periodic solution to this problem here, okay, in the maximal regularity class, the L2 maximal regularity class, which is this. So W is in this space, and P is in this other space, and Xi is there. So it's a maximal regularity class. But again, this is not the interesting thing is the following. Can be this fully linearized problem be solvable for any frequency omega? So let's go back here. Do we have any restriction to impose on this omega in order to solve this problem in this class? And I will show you, I hope in a kind of clear way, why this imposes no restrictions just due to the viscous effect of this force here. So, of course, if the FLP is solvable for any frequency, there is no resonance. If not solvable for any frequency, then you may have resonance. And we will show that the answer is yes, thanks to the damping effect of the liquid viscosity. So let's go back to the resolution of the FLP. So this problem here again. So what you do, you take this problem and you Fourier expand the W, the delta, the psi, excuse me, and P. And so you arrive to these equations here. So this is the Fourier expanded version of, for each component of the original problem, okay? So you see that this problem, of course, is of elliptic form, elliptic type here. These two equations are not decoupled, of course, right? Because there is psi k here and psi k there, and there is wk. So these are coupled as expected. However, you can use a trick to decouple completely these equations, that just due to the fact that they are linear. And so you do as follows. So you introduce some auxiliary field, this HA, this HI. Now look at the meaning of this HI. Basically, this HI solves exactly, as far as the equations, exactly the same equations as WK. But the interesting thing is that at the boundary, they're just equal to the unit vector isobi. Now, for this problem, it's an elliptic problem, very simple to solve. You can show that there are solutions in the beautiful space W22 with the gradient of P in L2. The important thing is the analysis of this force here. This is for the auxiliary fields, this is the viscous force, the corresponding viscous force. So it's a matrix because it depends on two indices, I and K. K is for Fourier, I is because of this. And you show that the quadratic form associated to this matrix has this expression here. So you see, you see three parts, but in fact there are only two. So this is a purely imaginary contribution, and this is the purely real contribution. Okay, so this has to do with the oscillation with frequency, and this is due to viscosity. Now, go back to the original problem for WK and PK, and you can see that WK can be written as a linear combination of this HK. It's a simple exercise, okay? So where the psi k have to solve this equation here, okay? So the system is decoupled now because I solve for this psi k if I can. This algebraic system, this is an algebraic system. So I solve for this psi k, replacing here, and I get the WK and PK. So I have decoupled the equations. Now the question is, again, first of all, this algebraic equation, I can rewrite it in this way, where K is exactly this previous matrix here, is this matrix here, okay, which is known because the HK are known, okay. So this is very similar, look, this is very similar to the equation that engineers, they try to solve, right, because given Fk, I have to find Xik, but now it is no longer, you don't have just the oscillation due to the structure, but there is this contribution due to the force of the fluid on the structure, right? This red part, okay? So the whole thing boils down to see, to check whether this matrix here is invertible for any omega. If m is equal to 0, so there is no viscous force, then this is not invertible. This is exactly what the engineers do, right? So this is not there. Fk, if m is equal to 0, this problem not necessarily is a solution in psi k if this omega squared hits the eigenvalues, k squared omega squared hits the eigenvalues of A, right? But now we have this extra term. And so the whole thing boils down to the invertibility of this matrix for any omega or not. And so this is the K lemma. So for any omega positive, this matrix is invertible. And you will see that is just due to the viscosity of the fluid. Okay, so let's prove it. So let's take the quadratic form associated to this matrix. and impose that this is equal to 0. We have to show that psi is equal to 0, basically, and you have invertibility. So now this equation here is equivalent to, thanks to the expression for the quadratic form of k that we have found before, this expression here is exactly this, the sum of these three terms. Okay? So this term here is the one that you observe in absence of the fluid. So basically this is what the engineers do. This is exactly the same term, right? There is no viscosity here. Now, these other two contributions, the second and the third, are due to the viscous force. And there are two contributions. This one here that is purely real. This one here is purely real. So it's of the same type as this one. And this one in red, however, is purely imaginary. And this is due to the viscosity. Okay? So this is the part of that component of the force of the fluid that acts in the same direction as resonance. So is the forcing term for resonance, let's say. But this part here is just a viscosity contribution. This is the gradient, the typical contribution to viscosity that we get from the Navier-Stokes equations. Okay, so this is real. This is imaginary. So of course, real part and imaginary part must be separately 0. And so you get that the gradient of psi I h k I, this summation, of course, is identically 0. But remember that the hki, they have, at the boundary, they have trace ei. So this has trace psi I ei, right? Which is the absolute value of the modulus of psi. Okay, so by trace, this is just a simple trace inequality. Psi, the magnitude is equal to psi I ei, and the psi I by trace inequality is bounded by this quantity here. But this has to be 0, and therefore psi is equal to 0, and you have the inversion of the matrix. Okay, and so you have no resonance, so the whole thing is solved for any omega. So as I said, this is the part that I guess everybody, also not fluid dynamicists, can understand very well. And there are other, of course, there is a bunch of other technical things that are interesting mathematically, but not as fun as this. I think this is the crucial point of the whole paper. I mean, of the whole paper directed to the absence of resonance. So now, conclusions. So what have we found here? So equilibrium configurations, they exist, are unique and stable as long lambda is less than some lambda c that you can give, I mean, that you can find. Local Hopf bifurcation may occur when lambda naught is greater than or equal to lambda c without restriction on the frequency. So local Hopf bifurcation is not responsible for resonance. So what are the causes of resonance that we're going to investigate, we're actually investigate as we speak? So possibly try to find a global conditions for Hopf bifurcation, so for larger lambda. So you're increasing the intensity of the wind, and maybe something different is going to happen. And also, and more importantly, I guess, from the physical viewpoint, is rotational effects. So we're assuming that this bridge can oscillate this way, up and down, sideways, diagonally, but we're not assuming, we're not including the rotation, which could be crucial for this kind of things. And therefore, we're currently working on this problem here. And at this point, happy birthday again, and I thank you for your attention.
Thank you very much for your really very interesting talk. I would like to see it more carefully and maybe discuss with you, because I think it's really very nice work. Very interesting. Yeah. Maybe you have some questions to put to yourself, because you always have questions.
That's right.
No.
Well.
Okay, but maybe
I already answered.
You have many questions, I presume.
And I answered myself already.
Thank you, Paolo, for this beautiful talk. Very interesting. So, I'm in touch with Filippo, and we discussed it many times about this. So at this stage, maybe you just drop the word at the end. You start thinking of the rotational effect.
Yes.
But is also, important the torsional oscillation,
Yes,
right?
one thing at a time.
One thing at a time, yes. But do you think that
In fact,
can be pushed up to
Filippo
the...
with some models, because he approaches the problem basically so far. He has approached the problem without involving Navier-Stokes equations.
Yeah.
So my contribution is to involve Navier-Stokes equations, which is more, so basically, so he has shown with a different model, not with this one here, that the torsional effects can be the cause for the collapse of Tacoma Bridge, right?
For example,
But the point is that to try to understand if Hopf bifurcation can hit this second eigenvalue that is the one responsible for the, and this is a big thing to go because it's, as you know, as soon as Navier-Stokes come into play, things become more complicated and more fascinating at the same time. So we're doing one thing at a time. For the next time, we're already working on rotation and see what happens if we can find resonance. If we don't, then we go to the torsional effect.
What about physical engineering experimentation in wind?
See, basically
what happens.
Daniele was saying and what Filippo already proved with a simplified model. So that is the torsional, experimentally, is the torsional effect. So basically the bridge can do this, but can also twist like that. Okay, and so if you...
This should be very bad.
Exactly, no, but it's interesting because so the first eigenvalue will give you, for a certain problem, will give you only steady bifurcation in this way here. So you have to go to higher eigenvalue to find the torsional effect.
Okay.
And in this context with Navier-Stokes, it's a fascinating, interesting.
For
problem.
sure, for sure. Thank you.
Not,
other questions? No, thank you very much
you're
again.
welcome.
Now, next speaker is Professor Dimitri Mugnai. He talks about on some mixed operators. Please.
So, thank you very much to the organizers for the invitation. It's really a pleasure to be here to greet a great mathematician that I have the honor, the pleasure to call friend. So, happy birthday. So, what I'm going to talk about is about two classes of mixed operators. So, what do I mean by mixed operators? In the first case, we consider operators of this kind, which are simply the sum of, let's say, the P Laplacian or the Laplacian, plus a fractional version of the Laplace operator. So it's something like this. All of you know very well what I am talking about when I speak of a fractional Laplacian and of the P Laplacian, but of course it's mandatory to refer to the book of Vicenzio for all the things that concern the fractional Laplacian, the book with Giovanni and Raffaella, of course. So in the first case, we consider this problem in which we have the sum of these two operators, so this mixed operator, and we look for non-negative, non-trivial solutions when the nonlinearity has a p sublinear growth at infinity. Of course, this is what we could consider the generalization to this operator for the celebrated paper by Bresis and Oswald, although there were studies for sublinear problems for the Laplacian starting from the 60s. In their famous paper, Bresis and Oswald consider the Laplacian, and they give a complete characterization for having a unique positive solution to the problem with the Laplacian, only using variational methods. And then there have been extensions to the case of the P Laplacian, or to general quasilinear operators with Nicholas, for example, two non-local operators with Pinamonti and Becky, but there are many, many contributions. So, let me go back to the original paper by Bresis and Oswald. The problem is this one, minus Laplacian u equals f, in a good domain. What is important is that you have a function f, which has some properties. In particular, if you fix the variable u, say you have a bounded function, what you need is that the quotient f of xt over x is strictly decreasing, let's say on the positive axis because you look for non-negative or positive solutions, and then you have a bound of this form. So from above, you know that the function f is bounded by something which grows not more than linearly. And what they show is that this problem P has, let's go to the solution, exactly one solution if and only if you have this condition which relates the first eigenvalue of the operator minus delta perturbed with a certain function. This eigenvalue must be less than 0, which must be strictly less than the first operator, the first eigenvalue of this operator, where these two functions, a0 tilde and a infinity tilde, are simply the values that you obtain when you get the limit of the quotient at 0 and at infinity. And of course here, since you don't know that a0 tilde and a infinity tilde are bounded because you don't have a global bound of this kind, the natural definition of L1, lambda 1 must be suitably changed according to this little change in the definition of eigenvalues. So recall that Bressis and Oswald had this estimate from above only. What are the key ingredients in the proof of Bressis and Oswald? First, they have a global elliptic regularity up to the boundary. You know that every solution of the problem must be of class C1 alpha up to the boundary. They have the strong maximum principle and the Hopf lemma, so they can take as test functions in the problem the quotient of the square of one solution over the second solution, and then they finally prove that actually the two solutions coincide. While for the existence part everything is variational, they look for critical points of the associated energy functional. For this it is important to study the structural results given for an associated eigenvalue problem with a weight which can change sign, and then they use the linearity of minus delta. If we want to go to the mixed operator, just think also to the case P equals 2, which is the simpler case. This point here is pretty much the same. It's not difficult at all. The linearity is good. The structural results for the related eigenvalue problem holds, but the problem is before. So in the first slide, this key ingredients part is more complicated. In the case P different from 2, of course, you cannot use the linearity because you don't have nonlinearity, but you have some nonlinear green identities which are good as well, for example, by Allegretto 1, and which are based again on the C1 alpha regularity up to the boundary for solutions of the P Laplace equation. So let me go to the mixed non-local operator. For instance, if P is equal to 2, so imagine that you have something like this, where here the plus is important for the maximum principle. So why studying this operator, for instance? The reason comes from sharks, for example, because I am in a biological department, and it is fun to see colleagues that say that sharks move according to an integral, which from our point of view means they move according to a non-local operator, so for instance the fractional Laplacian. This operator is not new at all. It has been studied since the 60s because it is well known, for example, that if you have a form of the maximum principle, then the operator must be the sum of, in the linear case, the sum of a Laplacian, say, some uniformly elliptic operator, say Laplacian, and a fractional Laplacian, say non-local operator. So these are not really new at all, but in fact they have been studied a lot in the last years. In fact, there are already some regularity results. For example, there is a recent result by De Filippis and Mingione in which they show that the solutions, that the minima of the related associated functional are C1 alpha. Then there are many results about the qualitative properties, the case of singular problems, shape optimization problems, overdetermined problems, existence and multiplicity results of solution. There are cases, they are studied also in the parabolic case, so now they are quite well studied. But the problem that we are interested in is this one. So we want to have the complete analog of Bresis and Oswald result. So we want to find necessary and sufficient conditions for the solvability of this problem where this f has p sublinear growth. So what are our assumptions? The first three assumptions are exactly the assumptions of Bresis and Oswald adapted to the p growth. The fourth condition is different. In this case, we need a complete growth assumption, also from below. And then there is a very terrible, annoying condition, which is in the model is always true, but we need it for some approximation methods. So we need to know that the nonlinear term is positive for small values of the non.
What is the value of p?
P is the general P Laplacian. P, because you see the problem here is the P Laplacian. Mathematically you do it for every P. So we have this big difference with Bresis, with respect to the paper of Bresis and Oswald. So F4 is global. And then this technical assumption, which is really annoying, but of course in the case of a power is trivially satisfied. So what do we mean by saying that we want to solve the problem? That we want to find a solution in the right space. Well, you know everything, I can skip this part, which solves the variational identity that you find testing with a a test function phi, but you want to know that the solution is non-negative and positive in a set which has positive measure, of course. So what are the problems that we find? First, we don't have the first step is missing because we don't have a global regularity result which holds up to the boundary. For instance, the result of De Filippis and Mingione says that solutions are smooth C1 alpha up to the boundary. But this is true only if these solutions are obtained as minima of the related functional, not in the general case. So we don't have this regularity result. We hadn't at that time a strong maximum principle for solutions of the problem. In the case P different from 2, we had no linear structure, but we hadn't any green identity either. So this means that the approach that Bresis and Oswald had cannot be adapted verbatim to this situation. Of course, what we need again is these two values, the first eigenvalue of the operator perturbed with the limit at 0 and at infinity. At infinity, with the global condition, now we have the right definition of the first eigenvalue with the integral of omega. So, with Stefano Biaggi and Eugenio Vecchi, we have these results, which is the perfect analog of Bresis and Oswald. So we have a solution if and only if the two eigenvalues, let's say at 0 and at infinity, are separated from 0. So this is the perfect analog. Unfortunately, to have this perfect analog, we need these two conditions. What are the ingredients of the proof in this case? We had to prove a strong maximum principle. So actually, we know that now the strong maximum principle holds. If you have a non-negative solution, which is so in a negative function, which is a solution of the problem, then it is either 0 or it is strictly positive in the domain. We have a global, let's say, boundary result for all solutions, and the uniqueness part, which actually is proved using all these these two annoying conditions that we need, because the fact is that we have to use an approximation method. We cannot work directly as Bresis and Oswald did. And in this approximation method, at a certain point, we have to pass to the limit and control things. And the only way to control these things is to know that you have a global bound on the nonlinear term, and that at a certain point we need that the nonlinear term must be positive near 0, which I repeat is clearly true if you have a power. But in the general case, we have to admit this, to insert this condition, because we essentially we don't have the Hopf lemma and we don't have the nonlinear gain identities that we have with the pure Laplacian, P-Laplacian term. A small detour. I said that I have considered the sum of the P-Laplace operator and the fractional P-Laplace operator. In this case, it is obvious that the bilinear form that you find associated to this operator is positive definite. But if you here put an alpha, which is very negative, of course, it is not true that this bilinear form is positive definite. So from now on, we concentrate on the case P equals 2. And if you want to consider this problem where here there is a very big negative, very negative alpha, it is clear that this operator is not positive definite anymore. So this means in particular that you have a complete lack of the maximum principle, for example. Nevertheless, you can develop a spectral theory, and you can study this problem when f has a superlinear growth or an asymptotically linear growth, or you can also use, you face the case of a resonant problem, which Paolo Galdi has just spoken about. So also here, in this case, it is possible to study resonant cases. And it has been done recently with some friends. So this is the end of the detour. In the second part of this talk, I want to concentrate on a new class of mixed operators, which have been introduced now, but which come from some considerations that have started 23 years ago, in 2000, by Silling, who is an engineering. So in engineering they have considered for many years many composite materials and many classes of composite materials. And it has come out that a good way to describe all this situation is that to consider not purely local operators like Laplacian or P-Laplacian or uniformly elliptic operators, something like that, but to consider operators in which, if you look at the stationary part, again, Silling says that the operator that you want to study must be written as a non-local term, say, so the integral over some set of a function which depends on the difference between the unknown and with a function that depends on the difference and on the distance of points. Of course, for us, it's immediate to think about the fractional Laplacian. No? And in fact, the problem that we consider, these are works in collaboration with Cluny and Gusella, who are some engineers from the University of Perugia, Eduardo Proietti, who is on leave for the Western University of Australia, and Patrizia Pucci. So the operator that we consider in the stationary case is this one. So C and K are just physical constants. You can put them equal to 1. It is not the problem. There might be also an external potential which has some mechanical meanings, but from a mathematical point of view, it's nothing because it's something positive and bounded. So it's nothing strange. And the operator that we put here is the regional fractional Laplacian. So it's the operator which is defined with the integral only over omega. And the mixed peridynamical problem that we consider is this one. So we have this equation which holds, it's not a mistake. Here you see omega, here you see omega 0, here you see omega 1. Because omega is the big domain, it is the body. You can think at the beam. So omega is the beam. And you divide the domain in two parts, omega 0 and omega 1. So if omega is the beam, you can think that omega 1 is the part of the beam which is inserted in the wall. So it is fixed. And that's why here we require that the solution, so the function, the displacement is identically 0 in omega 1, because omega 1 is the part of the beam which is inserted in the wall, so it's fixed. Omega 0 is the red part, so it's the interior part, the inner part of the body, so it's the part of the beam which is out of the wall, so it's the one which can move. If you think that the suspension bridge, this is the part of the suspension bridge which is free to move. I see that Paolo Galdi is looking at the picture.
I'm a little bit confused by the three domains. So the U, because you have the U that is defined everywhere, right?
Yes, it's the complete bridge.
Yeah. Oh, okay, so U is in the larger, is defined in the larger.
Yes.
Omega
Omega 1 is the part of the bridge which is fixed in the stone of the mountains, okay? And omega 0, the red part, is the one that is free to move, okay? So if we think to the fractional Laplacian that we are used to see, now we say that U is equal to 0 out of the domain. Actually, here the non-local boundary is not the complementary of the domain, but is this region omega 1, which is here. And actually, there are some obvious engineering conditions which must say that the part which is free to move and the one that is fixed in the wall must be far away. So the bridge is not simply touching the mountain, but is inserted in the mountain, and so that's why we need that a certain omega delta is can be omega 0 can be enlarged by a certain radius of radius delta, and you are still inside the domain. This is simply to say that you don't touch the wall and you fall down. So the natural space associated to this they call it a peridynamical operator, this strange operator which has a non-local boundary. It is simply the space given by functions which are h1, 0 in h naught, because you see the equation lives in h naught, as I said, and you have the Laplace here. And then you must add the part which takes into account the fact that you have a non-local operator which is defined all over the boundary. And so the function space is the intersection between h1 0 of omega 0 and hs of omega. First remark, it's very easy. If you give a datum, you always have a unique solution. This is clear because you find the minimum. A bit more complicated is when f is nonlinear. In this case, we consider f to be 0 at 0. and with some conditions. These conditions appear in this way in a paper with Proietti-Lippi, but actually are an improvement, in the case p equal 2, of a condition that we introduced with Nicholas some years ago, and which was again an improvement of the monotonicity condition of Zhang. So we require a sublinear growth, but a superlinear growth at infinity, and then we have this quasi-monotonicity condition. In fact, if we look at the difference between FTT and twice its primitive, it's not completely monotone, because here there is a coefficient which can be larger than 1, here there is a perturbation term, but anyhow it's a condition which is quite general, and which is of course more general than the Ambrosetti-Rabinowitz condition. So, for example, something which behaves like this, which doesn't satisfy the Ambrosetti-Rabinowitz condition. So, what do? We are looking for solutions, so functions u which verify this integral equation, of course, and which are the critical points of this, the associated energy function. Under those assumptions, we find that if this assumption holds, then we can find two solutions which have constant sign. One is strictly positive and one is strictly negative. We have some problems with the existence of a third solution. Further developments about this mixed peridynamical operator, which I will not discuss here, is the study of spectral theory. And I give only a hint of what you can do about evolution problems, because, of course, from the point of view of engineering, the study of evolution problems, as Galdi has just said half an hour ago, is fundamental. So imagine that you have an equation, an evolution equation of this form. This is a very simple example just to understand what is the nature of things that one can do. So you have UTT minus the operator. Here you have a damping term which is multiplied by any power, positive, negative, a priori, what you like. Plus here there is also a continuous function which is bounded below by a positive constant and bounded everywhere. The potential V is supposed to be continuous with a positive continuous derivative in T. And here, just because here we put the power to the alpha, think that the interval you are interested in is 1 plus infinity. It simply means you have a non-degenerate function over there. You can define the energy function associated to the solution. If you want, you can put some C, some K somewhere, and you can think that they are one. And what we prove is that if alpha, for example, if modulus of alpha is less than or equal than 1, then all solutions of this problem are stable. So the energy goes to 0. This is very important from the point of view of stability, as the one that Paolo Galdi was saying before, of course, because it means that as time goes by, the vibrations and the displacement tend to 0, so the movement disappears. And to prove this theorem, we have taken some ideas from the paper by Pucci-Serri in Atto Matematica, which was developed by Pucci and Saldi some years ago. The last result, which is very useful again in control theory, is the fact that if you take a solution of this problem, what to do in general if you don't have this condition? What happens to solutions? And what is interesting to know is that solutions can go essentially to any possible limit, in the sense that A function p is said to be attainable if there is a solution of the evolution problem which goes to psi as time goes to infinity in the L2 sense. And again, taking another idea of Pucci-Serrin, we can prove that the set of attainable functions is dense in L2, of omega 0, of course. So that's what I wanted to say, and I end with happy birthday again. Actually, I was looking for another picture that we took at our home, when the one in which you play Biliardino. I don't know the English for this.
We understand this.
Okay, but I couldn't find it. I don't know where it is. Table soccer.
Thanks for your clear and interesting conference. Oh. Thank you very much for your interesting conference and clear also. Other questions?
Of course.
So, no, concerning just the previous. Sorry. No.
No.
Okay. No, the previous two slides. So again about the so this one here. So here one shows that when alpha in absolute value is less than 1, then you have that kind of asymptotic behavior. Now, of course, the next problem that you want to solve to the next slide is under assumptions that are different.
Alpha is not less than 1.
Exactly. So that's the thing. So alpha not necessarily less than 1. Not necessarily. It must be strictly greater than 1.
You're right. Sorry, larger than 1.
Exactly, because otherwise.
Yes, larger than 1.
Yeah, right. Of course, that's okay. Now it's clear. So basically, you are trying to find a kind of an attractor for the whole thing, right? Okay. Now the other question is just curiosity. So the first problem that you started with the P Laplacian, what happens if one is a P Laplacian and the fractional operator is a Q Laplacian? So what?
Don't know.
What does the shark say?
Sharks only see 2.
Okay.
So sharks are happy with the 2. P equals 2. Where is it? So
yeah. Okay.
In
So
fact, you see, the prototype is this one.
yeah. Okay.
But actually, we didn't check about it.
Yeah, but what would change? I'm just wondering what could change if you use 2 different P Laplacian. One that helps, for instance, and the other that is bad.
Now, I would say that I can do this one for sure. I can do this one. Let me think if P is different from Q.
The maximum principle, I don't know.
In fact, that's what I'm thinking. I don't know. Now I don't know. In fact, now this is the point that I'm pretty sure that I can do this. I can do this.
Yeah.
I don't know about this one.
Because,
maybe I don't know.
I'm looking from a different perspective. Namely, I'm looking for I see this problem as a non-Newtonian fluid. I'm looking at this like that, and so basically I can see one part that is shear thinning and the other part is shear thickening. That could be true in a non-Newtonian fluid. And so one that helps somehow doesn't create singularity, the thinning part, the thickening part, and the thickening part, and the thinning part that. Yeah. So just and also the final question is why U greater than or equal to 0 is important to the shark.
Because as a solution,
so
you mean?
Basically, okay, so what is the, sorry, let me rephrase, excuse me. So what is the relation between the solution and the shark, U and the shark?
U is the density of the population, so it must be positive.
So, okay, I see, nothing to do with the motion of the shark, so just the population.
No,
Okay,
the density of the population.
Okay, that's why, of course, so it has to be greater than 0, otherwise the shark is not happy. Okay, all right, thank you.
No, but I can say about this mixed operator, I show you briefly another thing in the problem here. What is fun, for example, fun, it's not fun, what is strange? We have some numerics, where it's, one could think that the Laplacian wins, because one expects that the Laplacian wins. In fact, it's not true, because, for example, we have some pneumatics which shows that the regularity is not as nice as one can expect for mixed operator, for example, in the other case. In this situation, it seems that the fractional Laplacian wins. So, when you mix operators...
Win against regularity.
Against regularity.
Yeah.
Because maybe you can say that il video autori sono ingegneri, no?
No, l'ho detto.
L'hai detto,
sì, sì,
scusa,
detto.
perché col fatto
Sì, sì.
però...
Yes, Klein-Gordon-wave are engineers.
Perché l'ascensore è rotto.
No, I said that they are engineers from Perugia.
Is this fine? Other questions? No. Okay, then. Thank you very much again. Next speaker is Professor Diaz.
Non vedo.
Talk about
This is
magneto-optics
for
effects
the-
in the motion of the director field of
right,
a
and
nematic liquid crystal.
this is for the pointer. Yeah. Okay, thank you very much.
Then,
Okay.
please.
I wish to thank the organization for the kind invitation, especially Daniele, and congratulate Professor Radulescu for his birthday. Thank you very much. So I apologize, my English is not very good, but I want to speak a little about this problem. It was a problem that is motivated by the work of experimental physicist Marinha Martins. That is the first time I work with a experimental physicist, and it is very interesting. It was a guy that I know 20 years, 30 years, but is very, very active and knows mathematics. It's rare in the experimental physicists. And also with Paulo Amorim, that was one of my undergraduate students, and after he passed the thesis in Paris with Philippe Le Floch in hyperbolic problems, and also in the numerical problems. And so the calculations that are made in the paper are made by Paulo Amorim. And so with this title, you see that these words was written by the physicist. Maybe you know that what is a nematic liquid crystal. It's an isotropic uniaxial fluid made by long, rigid molecules that are positional disorder, but in a sort of orientation that is described by the so-called director. And a great number of technical applications that are related with the data display in nonlinear optics that use thin films, two-dimensional films of nematic crystals in between two solid surfaces. And in this device, local direction of the optical anisotropic crystal represented by the director is determined by boundary conditions and can be modified if you apply by application of electric of magnetic field. And there is these interactions between these fields that you can optimize the performance of the device. And so in this talk, you want to study the mathematical analyze the model of a motion of a liquid crystal coupled with the Schrodinger equation. This type of model, this short wave, long wave interaction, is motivated by a seminal paper by Benning, where the general theory of the short wave, long wave interactions are presented. Since then, other variants are studied, for example, in the paper by myself and Hermann Fried and other authors. For hyperbolic conservation laws, the perceived equation, linear equations, coupled with the semi-linear Schrodinger equation. In this presentation, you consider the dynamics of a nematic liquid crystal as long wave in one spatial dimension. The function rho, x, t, describe the director field of the liquid crystal, and the rho measures the angle of director field to the x direction. You are in 2 dimensions, you are now a magnetic field. You want to study the motion of the director field in the nematic liquid crystal, submit it to a constant strong magnetic field with intensity H, with intensity H, this is the module, and also a laser beam, assuming the previous simplifications and approximations. This is motivated by the experimental models that some physicists, namely Farinha-Martins, and yields to a coupled system where the first equation is a Schrodinger equation, in our case, Schrodinger equation with the presence of external constant magnetic field. And you can see this sort of Schrodinger equations with the magnetic fields in the book of Cazenave, these principles where they are related to this kind of problems, and also about Maxwell Schrodinger models. You consider the complex valued function u, the x and t, then it represents the wave function associated with laser beam and the presence of a constant magnetic field, and verify the equation, Schrodinger equation. Previous ideas taken together give the system that you can see. Sorry, not. This system and the consideration we have the Schrodinger equation and the hyperbolic equation for the angle rho, and E is the imaginary unit, U is the complex value, V is the derivative of rho, and this is the constant number. P is positive, and the given constant, and with the initial data. This is the Cauchy problem that we want to see. And the function, this function is a quasilinear function. It's a quasilinear problem because you have the derivative, x derivative of this polynomial. Okay, V is the derivative of x derivative of rho. Rho is okay, the x derivative. So you have an hyperbolic system and coupled with a Schrodinger nonlinear Schrodinger equation. These constants are positive in the flux function. We deal the motivation of the treatment with the angle are made by the following simplified model, okay, with the function C rho, general function. In this case, for the nematic liquid crystal, the C is given by that function, okay. And alpha and beta are the elastic constants to the crystal, liquid crystal. You can see a paper by Hunter and Saxon that deals with this kind of constants. And this is a quasi-linear hyperbolic equation. Short time, you won't see what happens, but of course, it's a quasi-linear system, and so you have a blow-up result in finite time. And with some restriction on this function, not this in particular, this particular case can be applied for these results. There are very important and difficult results for with restrictions on C that has been published by Ping Zhang and Yuxi Zhang in 3 very good papers in the communication partial differential equations, the Shai for Chanel mechanics and analysis, and analyse non-linéaire de l'institut Poincaré, application, the compensated compactness method, Murat, Artar, and Iperna, and finally, by a method of characteristic with changement, very difficult method, was solved in the general case for this model. You know, it's very difficult, this term, okay? And by Bressan and Yuxi Zhang, more recently, by a difficult direct method. He now made some simplifications on system motivated by the arguments in paper in the physicist paper by Farinha-Martins and the other collaborators. And you are using the notations of this paper. And so, if the elastic constants are similar, quite similar, the two important, the director field satisfies, it's easy, the physicist in his paper, is this kind of relationship. And so, where H is the intensity of magnetic field, K is orthogonal to the director, and the K is the anisotropy of magneto-susceptibility. And so, this is setting this constant gamma to this. You obtain by integration. It's very easy to obtain that, and with that normal exigence for rho or rho x, and assuming that situation, alpha greater than beta positive and alpha similar to beta, not very far from beta, and with this constant, this is not a constant, it depends only on t. You get finally the value of the, it's not difficult to obtain, the new value for the situation. It's this equation, okay, with lambda equal to that. This is flux function with that these restrictions. And our main goal is to prove the global existence of a weak global solution for the initial problem for the quasilinear system. And for that, he applied vanishing viscosity method for regularized system with the physical viscosity, and the composite compact net method developed by Schiera and Schiera in the paper that has been never published, but I don't know the reason. But it's very interesting, this paper. I will show in the end the bibliography. And for that, to introduce, for example, you can see in the book of Cazenave this kind of spaces that are related to the magnetic field. And we introduce also the space that for the energy that is with that definition. And here, this is related with the flux function. In particular, if V is in H1, this is finite. In the next session, we prove the following existence theorem for the weak solutions of our previous system for appropriate initial data. Sorry, it's terrible. Okay, this is the theorem. This is you separate the two equations. Okay, and this is in the normal formulation for the Cauchy problem for weak solutions. Okay, and so to note this formulation is, of course, you obtain immediately that the t derivative of rho is W. And so in the next, you go quickly because you have no time, for the proof of the existence theorem for the viscous problem with physical viscosity, and after we prove some compactness arguments for the proof, and finally, you show some numerical simulation made by Paulo Mourinho. Okay. The estimates are not very difficult, but there are some tricks. So he approached by it's just very normal to solve to study. You know, this is the parabolic physical parabolic approximation of this Steve. He approximate, of course, only that equation. In fact, the technique by Bressan and Zhang cannot be applied because you have a coupled system, and the method of characteristics is not good for a Schrodinger equation. So you cannot work on method. You can work with the method by approximation. Okay. So the spaces are a normal space that you have in this problem, and also you have the conservation of mass of normal for a Schrodinger operator. And after you have the energy perturbed, of course, by the epsilon, energy associated to the system. And so there are some calculations, I don't bore you with this kind of calculations, that energy estimates and more sophisticated estimates, but not very difficult, that are similar to those that are made in another case by Schiera and Schiera in this paper, I will show in the end. And after you continue with these estimates, there are a lot of estimates to obtain finally with after there is a you need a certain point because you have in the energy you have a problem because you know this is a negative. This term is not they have no sign because rho you have the sign for rho. So you must estimate this term is not difficult because you have Gallardo-Nirenberg and you made some compensation. You see, for example, here you see the normal estimates, and so this term it disappears in the estimates problem. And you continue to make estimates, and these estimates, of course, you have omitted the epsilon in the functions, but the epsilon, I keep the epsilon here, okay? And you continue to obtain estimates like that. And finally, you obtain these estimates, very important estimates. This is the t derivative of rho, this is the x derivative of rho, v. And you obtain these estimates, a local in time estimates, but epsilon, you know, you must have here epsilon. Okay, this is the main estimate to apply the technique of Schiera and Schiera. And for the proof, this is quite normal. For the proof of the theorem of you first you prove the existence and regularity and certain regularity for the approximate system. For that, this is a fixed point, convenient fixed point theorem that you can choose normally the usual spaces to apply the fixed point theorem. And of course, you have fixed point theorem, and it's very important the fact that the operator A is the maximal dissipative. You have a semigroup associated to that, and so you can solve the problem as usual. And it's a consequence of Banach fixed point theorem in the covariant space for local. And so you have local problem solved for the approximate system, and after by further estimates on derivative on t, you can obtain a normal solution for all t in the 0 plus infinity for the approximate problem. So this approximate problem is solved, and after it's easy for the estimates, previous estimates, that u epsilon is bounded in this space, and the derivative in t also bounded in that space, and you can apply the local injection in compact injection of Aubin that you can see, for example, in the book of Lyons, Quelques méthodes. After avec the diagonalization method, you have a subsequence that converge for U and L infinity that, okay, with that convergence. And after, to apply the compensating compactness method now, you must have some information on the system, on the previous system, and for the convex entropy flux for this system, with some properties to apply the results of Schiera and Serre, but this can solve this problem, it's not difficult. And you can deduce that this term belongs to a subset of this space, and apply the composite compactness of Schiera to conclude that it's a precompact in this space, and there is a subsequence that converges in that spaces to that, and so the solution converges, whereas the solution of the weak for a weak solution of the previous system, the original system. It's not very complicated. It's a technical proof. And so for the last 10 minutes, I suppose that I have, I am going to show some numerical experiments made by Paula Murin. It's very interesting. use the formulation, the approximate formulation, of course. You cannot work it with a parabolic system. You work with the parabolic approximation with very little epsilon. Okay? And so a numerical scheme introduced by Paulo Amorim is the normal one, third order Runge-Kutta method of time evolution along the standard finite difference for the spatial discretization. You see the problem to the large enough, of course, interval, and take spatial data with the convenient spatial data, discretize as usual. And we solve numerical the ordinary differential equation, this numerical differential equation, and use this kind of method to with the steps tau to giving an approximation solution. And after the numerical results for special, of course, special initial data that are convenient, and this one, and the physical parameters are the introduction in the introduction, or the down in the introduction, and you take the elastic constant like that, you know. That is not very different, and alpha and beta are calculated as usual by that, and in the gamma depend on H, and determined by one formula, anterior formula, and we set these values and the numerical parameters, and then plot the numerical solution with magnetic field. Okay, H equal to 2. The solution of Schrodinger equation remains in the bounded region of the x-axis with an oscillatory behavior due to the interaction with quadratic potential. This allows an interaction with the mathematical field. It can be dilated. You'll see now the figures. Okay, it's first figure. Okay, second figure. In the case, it is what you have. There are definition of the values are here. Okay, this is the velocity of the derivative. The rho. This is rho. This is the modulus of u, module in the real part of u. You know, and this is for the case h equal to 2. And this is the case h equal to 10. You know, it's quite different. The interaction concentrate here, okay? And this is, you can see the influence of the laser beam on the nematic field. This is case with that data, initial data, and the right, this is for this interval of time. You have here x, t, and this is the value of rho, okay? In the value of u. And if you increase the magnetic field, the situation can be seen here. It's very important. In fact, you have, but because there are experimental cases where you have the laser, you have only the part, the second equation, and not the laser. And the situation is, sorry, you have not the laser, see, a laser beam, you have not laser beam. And with the laser beam, we increase the interaction near, you know, if you augment the magnetic field in the laser beam, you change the interaction, and it can be seen here. It's interesting. And of course, I can say something theoretical about that, about the results. The results suggest that within this framework, the presence of the laser beam present by U has a perceptual effect on dynamics of the nematic field. Recall that when you focus the present work is mathematical. These illustrative numerical results cannot provide precise physical conclusions. However, despite our simplifications, they do suggest that the introduction of a laser beam may have an influence of the type of liquid crystal phenomena studied by Faria Martins and collaborators. they fall outside of scope of present work. Also, results suggest that it might be interesting to compare our simulation results with existing experimental work on the magnetic-optical behavior of nematic elliptical crystal, like in the papers that you can see now in the reference. There are papers for liquid crystals. This is a paper of Benny on the general theory of interactions of short and long waves. This is just a paper on the interaction of nematic crystals, magnetic-optical, and Bresson and Zhang, a paper, a very important paper, application mathematical physics will solve the problem without the Schrodinger equation. Kasnav book, Jen Prost is physical liquid crystals is for general considerations on the crystal bits. The two papers by myself and Figueira and Fried about the existence of weak solutions and the case of one equation of the Burger's equation. And this is the case of a system. And the paper of Teresa, the paper of Lyons, paper of Martins, another paper on physics, another paper on magnetic-optic effects, and the paper of Schiera and Serre. This has not been published. It's a preprint with a lot of citations, but I don't know the reason. Schiera is not. He was a very strong mathematician, but rapidly he left mathematics, and so Serre, I don't know what is the problem. As in fact, they don't know publish the paper definitively. And it is the three papers of Zhang and Zhang that are very important for the system without the Schrodinger equation that give the ideas for the application of the Tartar-Murat-Diperne method compensating compactness. And that's all. Thank you very much.
Thank you very much for your very nice presentation. And I must say that I know very well Farine Martins. He's a strong physicist that he knows.
Nova University, Lisbon,
yes, but he's
science materials department.
He's a quite strong.
Materials of science materials.
Yeah, he
experimentalist. But he knows mathematics.
A strong experimentalist.
It's very interesting the discussion I have had with him. It's I can't have the time to. It's very curious. It's the first time I have worked with. I have worked with theoretical physicists mainly, because it's very interesting. But with the physics.
So applied things, no, it's not your tradition.
It's first time.
I know. Questions? But you are obliged to do.
You are obliged to do a question.
No, it's very, very interesting. I mean, the whole topic. So, okay, so what you find numerically is a kind of, so when you show those pictures, basically, exactly. So you want to see the influence of the magnetic field, the laser, basically, on the direction of
yes, it's a close question. We sent this paper to partial differential equation and application. They have two kinds of reference: the mathematician and the physicist, theoretical. I don't know. And after a first revision, the mathematical this okay to the Ben, but the physicist don't like the exposition. He obliged us to change the title and to put more physics in the description, namely in the introduction that Farine Martins made. And you are waiting for the answer, because if he accepts the modified physics that he put in the paper, it's not normal, because it's in fact it's a mathematical journal. But it's interesting because they choose two kind of reference: a reference that is mathematician and a reference that is more physicist. Yes, maybe.
But you don't know what my question is.
Yes.
Right. Okay. No. So those shots, okay, those screenshots that on the numerical aspect. So these are kind of steady situations that you observe?
Yes.
Okay, so this means that your equations, they have a kind of attractor of kind of, they tend to some steady state?
Maybe, I don't know, but this kind of, maybe this depends on the, it is an interesting problem because with when it's quasi-linear, you have no uniqueness for the global solution. So maybe you have some sort of this kind, but I'm not sure.
But did you analyze the steady state of this problem here?
Yeah, yes, it's in only a case, the case of the elastic constants are equal, you have a semi-linear problem. So you get the global existence of the problem, okay? And you can prove the existence of
the steady solution.
Of stationary state.
Okay. A perturbed stationary
And
state.
yeah, and you can prove. I'm not sure it's a problem in working. You are now working in that. We are to prove the partial orbital stability of this kind of stationary states.
Yes, because that's what I'm expecting.
Yeah.
Because in what
But
really it's
only in the semi-linear case, that is, you don't, the quasi-linear case, you have no global solution. You can prove also local solution by Cato's theorem. Applying Kai's theorem for hyperbolic systems.
What is interesting from the physical viewpoint is that you apply this laser and this director stay in a certain position.
Okay.
So everything should be steady and stable.
Yeah.
So that's why I was wondering if the first thing I will study is the steady state, if there exists.
Yes, it's very important in physics,
Yeah,
but
exactly.
but I insist in the semi-linear case they have studied. The physicists, in general, in the semi-linear case, they put the two elastic constants equal, and the quasi-linear term disappear. You have only a wave equation. Okay.
First, I would like to thank the organizer for the invitation, and let me say I'm so glad to be here for the birthday of Vicenzio. And a remark about the title. Actually, the problem are not 3 or 5, but 5 was too high as number. Is a little bit. It can appear a little bit pretentious to speak about 3 problems in half an hour. But actually, I will speak about one problem and several variants. Okay. Now, at first, I would like to do my best wishes. So, tanti auguri di buon compleanno, Vicenzio. And in Italian, we say that chi trova un amico trova un tesoro. I'm really glad about your friendship. Okay. And these are the fireworks, because we had the cakes yesterday, today we have fireworks. And now let me start about the scientific part. Okay, I will speak about essentially a couple of papers. The first one is more or less a book. It's a long history. The American Mathematical Society takes a long time to publish a booklet. And the first paper is in cooperation with another Italian mathematician which works in Germany, Delio Mugnolo. And the second one, I will speak more on the second paper, which is still in preparation, in order to have your advice on some impossible improvement. Yeah, especially from Paolo. Okay, now the first problem. In this first part of the lecture, I will not give the physical motivation. I will just put the problems on the blackboard, because there are many problems to take account about. This is what I call the Eulerian model. So you see, we are in an open-bounded, simply connected domain of R3. And the boundary is, let's say, C3, C21 or C3. Which is not optimal, but this is the main problem. Now, the boundary, there is a partition of the boundary into gamma naught and gamma 0. You have different conditions on the 2 parts, and gamma 1 is non-empty. Now, in this Eulerian model, we have 3 unknowns, P, vectorial V, and V. I apologize for using the same notation, but in this way, I have to use the arrows. I like very much arrows.
Yes.
Yeah. And all the unknown are complex valued. Since the problem is linear, this is normal. but the coefficients are real valued, and mu and sigma are uniformly positive. Okay, this is the actual normal. B and rho naught are positive constant. The divergence and the curl operator are the standard one, like the gradient, while on the boundary we have the Riemannian version of the gradient and of the divergence. So this is the Eulerian model. Now, in the sequel, I will also consider the constrained Eulerian model, which is the same problem with an integral condition. Please note that there are no initial conditions. This is just the evolution equation. As to my knowledge, this Eulerian model has no mathematical literature. So as far as I know, we introduced the model in the paper with Delio. If you know some reference, I will be glad to know, to have news about them. Now, the second model I'm going to speak about is the Lagrangian model. And the assumptions are the same, but we have just two unknowns, R, which I'm going to call displacement, which is a vectorial unknown, and a small v, which is a scalar one. Because of the second equation, in the first equation, the gradient of the divergence is the component-wise Laplacian. This is something which is well known. I didn't know before, but I discovered. So this equation is a wave equation. Like the second one, they are coupled in this way. You can see you can just writing everything in terms of the displacement, but the mathematical equation is not so beautiful. It's better to watch to this as a system. Okay, the third model is the potential, what I call the potential model. We have the same assumption. Now we have two unknowns, u and v, which are both scalar. And in the sequel, I will also consider the constrained potential model, which is the potential model with another integral relation. This potential problem is not new, it's well known in the literature, as it's called wave equation with acoustic boundary condition. And that actually it was the starting point of our analysis, and the first paper is devoted to the potential problem under more general assumption. Now, some reference of this potential model. The acoustic boundary condition have a long history, starting from this paper in the 50s, dealing with the case of half plane or half space. Then the problem became famous about this, after these papers of Bale and Rosenkranz in the 70s. And then there is a large literature, essentially, when the boundary is locally reacting, which means you don't have the boundary second-order operator. You don't have the Laplace-Beltrami operator. Now there are some references also for non-locally reacting boundary, so when sigma is positive, but most of the reference deal with the problem Dirichlet homogeneous boundary condition, while we have Neumann boundary condition on gamma naught. The aim of the study of the book was to study these non-locally reacting boundaries without any Dirichlet boundary condition. Dirichlet boundary condition is very good from a mathematical point of view, but as I'm going to describe, has no physical meaning for this problem. Now, physical derivation. What this model tries to describe are small acoustic phenomena. There are essentially two models of acoustic phenomena of small amplitude in theoretical physics. This is not my modeling, the physicists did. The first one, which is in this book, a book in theoretical physics in the Landau-Lifshitz, which was the Bible from my generation in theoretical physics, in this model they used an Eulerian approach. And it seems to me rigorous, according to the standard of theoretical physics, of course. The second one is given in a textbook which are for younger students, let me say, so in which they use the Lagrangian approach, and it looks mathematically less sophisticated. Now, starting from scratch, acoustic phenomena are described by physicists by a first-order linear perturbation of the equation of motions. Usually first-order perturbation of nonlinear equation are too rough for physicists. But what they say is that this linear perturbation represent, well, in good way, many acoustic phenomena. Indeed, acoustic pressure is very small in relation with normal pressure. So this pressure is 10 to minus 4 is the acoustic pressure of a rock concert. So in this room, we probably reach 10 to minus 5. That's why they can use this first-order linear perturbation. Now, this Dutch physicist proves that from the physical point of view, the two approaches are equivalent from the physical point of view. So what they do is that they cut everything up to the first order. Now, let me describe a little bit the Eulerian approach, which is the, how to say, the most general one in some sense. Okay, what we are saying is we are in an open and simply connected region, which is bounded by some boundary, which is filled by a fluid. Now, the fields describing the fluid are V, which is the velocity of fluid particle, P, which is the pressure, and ρ, which is the fluid density. All are functions of position and time. In our model, a part of the boundary may move, so omega should depend on time. But for small perturbation, they neglect this dependence. Instead, V represents the small deformation of gamma 1 inside omega. I have a picture after this. And so in the direction opposed to the outward normal vector field. Now, physical assumption. The fluid is homogeneous, ideal, compressible, but thermal effects can be neglected, and viscosity effect can be neglected. So it's the orthogonal situation to the Navier-Stokes. I'm sorry. It's not mine, the model. Now, in absence of sound, the fluid is at rest. So nothing is moving, with uniform density and pressure. So this room can be a good model. Gravitational effects are neglected. Otherwise, the density can be not uniform. Now, this is a picture. So this is this room. This is in this picture, gamma, there is only gamma 1. We don't have gamma naught. So the particles of the fluid are moving. V is the small deformation inside, and we have this field. Okay, and this is we are in a bounded domain, so this is an accurate picture. Now, they start from continuity and Euler equation. In this equation, you can recognize Navier-Stokes. Unfortunately, now it's going to disappear. And in the acoustic phenomena, they consider small perturbation in this way. So the pressure, there is this small perturbation P, and the same for the density. They are very small. Now, they start from Hooke's law. So they say that the perturbation of the density is proportional to the incremental pressure under this adiabatic compressibility factor as a physical constant. Now, up to the first order, this equation can be written also in this way, using the infinitesimal volume strain, and you get this equation. Now, physicists use this bulk modulus, B, so they rewrite Hooke's law in this way. Now, the standard first-order approximation in theoretical acoustics is this system of two equations. Since the density and the pressure are proportional, we can rewrite the two equations in this way. Now, this is from textbook in physics. Now, let's discuss a little bit boundary condition. In boundary condition, this is the boundary. Gamma naught does not move. Fluid particle cannot penetrate in it. So on right, the boundary condition in this way. Gamma 1 can move, but the fluid particle have to move with the boundary. This is essentially the horror vacui assumption. And in this way, you get this boundary condition. These are standard conditions in fluid mechanics. Now, the motion equation of gamma 1 is essentially derived by Newton's second law. So the force acting on the boundary are the excess pressure, the damping, if there is a damping, otherwise delta is 0, and an elastic response. In our model, the elastic response is this one, so it's a combination of a membrane response and a spring, a pure spring response. When sigma is 0, you just have a pure spring response. And this is the question you get. If you put all together and you remember that this has to be rotational, you get the Eulerian model. So this is the first model I wrote before. Now, what is the just... Is it rotational because they say there is no viscosity effect, so the cannot is at rest. So it just yeah yeah, this is what they write. It's not my responsibility. They take a rotational.
So it's potential.
Yeah, of course. I'm going to relate with the potential problem. This is for the potential problem. And now, what is justification of the constrained Eulerian model? They write a generalized Hooke's law in this way, and they use at the infinitesimal level. Now, it is an empirical law, which is verified at a macroscopic level. If you try to write the Hooke's law, in our case, you do average, and what you get is that you have to add a macroscopic Hooke's law. By adding this macroscopic Hooke's law, the system looks physically more precise. There are some strange solutions which appear when you don't have this condition. But I don't have to describe them in this talk. Now, the Lagrangian approach. In the Lagrangian approach, X is the Lagrangian level. Is the position of a fluid particle a million years ago at some reference time. R is the displacement, so it's the difference between the position of the fluid particle and the original position. Omega is as before. Now, omega, since it's the reference domain, doesn't move, but the fluid is in this omega t. Now, the fields are the same. We do all the same physical assumption, and they prove that from physical point of view, like first order approximation, they are physical equivalent. And so, in this way, they rewrite Hooke's law in this way. Now, they rewrite Euler equation, or they just use Newton's second law. And since up to the first order you can confuse these two terms, you get this first order approximation. And this is the first order approximation in textbooks. Now, the translation of the boundary condition, since a fluid particle originally at the boundary have to move with the boundary, and the velocities, the time derivative of the displacement, they translate into these two conditions. Now, what is delicate here is that we integrate the first line starting from the reference time. At the reference time, r is 0. There is some physical consideration to do on this aspect. Please take into account in the equation there is no acoustic source. So if you start with r equals 0, the only solution is 0. But there is something which is unmodeled. Now, since the condition of irrotational of V translates into the condition of irrotational of RT, integrating from the reference position, we get this condition, and this is the Lagrangian system. Now, in the Lagrangian system, there is still the pressure, PL, but you can see from the first equation that you can put out the pressure by replacing with this term, and this is what we did to get the Lagrangian model. That physically is the physically relevant field, but unfortunately, mathematically is a good idea to put away. Now, how much time do I have?
Say 15 minutes.
Okay, now I will start to do some mathematical result, unfortunately. Now, what is really difficult to deal with three problems together is notation. So, I introduced the phase space, which is this one, and the solution space, which is x1, and the PC version is for the constraint problem. So these are the spaces. Now, strong solution of the potential problem and of the constrained potential problem are solution in x2, and they satisfy the equation almost everywhere. So everything is quiet. Now the problem is that is more interesting from a physical point of view to consider solution in x1, which is the space of the energy space. In this way, you have to consider that the U and V satisfy the problem in the sense of distributions. Now I have to introduce the initial value problem, the Cauchy problem, to give some well-posedness. This is this way P naught, and P naught C denote the corresponding initial value problem for the constraint problem. So the first result is that if you start into this space, you stay into this space, which means that the constraint problem is just a subcase of the general problem. So it depends where you take the data, the initial data.
I'm lost. This notation, how does it compare to the notation that we were using before? So U is the R?
Now this is for the potential problem.
So you already put it in a potential form?
Yeah, I have three problems. This is the potential form. So I'm starting from the potential form since I have a mathematical result for the potential problem.
So this is something that you're studying, and then you will see how it relates.
Yeah, at the end, at the last, before the thanks. Yeah, there is a jump. There are three problems. I started from the last one. Since from the mathematical point of view, we started from the last one. Yeah, so this lemma says that the constraint potential problem is just included into the problem. Now, the second result says that weak solutions are unique. Okay, so you have to prove uniqueness of these distributional solutions. Now, the result, which we proved, which is one of the results we proved in the first paper, is that the problem is well posed in the Hadamard sense. This means that it generates a strongly continuous group on the phase space. Moreover, you have regularity. We also have regularity result, but you need compatibility conditions, so it's better to skip here. Now, the same conclusion apply to the constraint problem. And I call T the first group, and the restriction group is TC. Constrained group because the space is reduced. Now, okay. Now, let's go to the Lagrangian problem. Let's go back to the Lagrangian. I will go in the reverse sense. In the Lagrangian problem, I need a phase space, a solution space. So, we have to consider space of an irrotational vector field, distributional in some case. This is the space in which R and V lives when n equals 1. In this space, I also put the boundary condition inside the space. The phase space is a product, of course, because you have to take into account first-order derivative, and this is the solution space. So this equation, the boundary equation, are stable in the sense of Lyon, so they are included inside the space. Now, strong solution satisfy the problem almost everywhere. Now, what about weak solution? What you get is that using semigroup theory, you are able to prove the existence and uniqueness of generalized solution, but you have to characterize generalized solution. So I gave this definition of weak solution. They satisfy this distributional identity. You can see that in this identity, I need that the test function are CR minus 1, not CR. And that's why I need R is greater or equal than 2. This is the main problem, main unsolved problem, but there is no way to improve. Now, the initial value problem for the Lagrangian problem is this one, and the solution of the Cauchy problem is our solution of L, and the initial conditions are taken in this space in which there is a continuity sense. Now, the interesting proposition is this one, is that if the divergence of R has a trace sense to the boundary, then the couple is a weak solution if and only if it is a distributional solution of the two-wave equation. Please note that in the second equation, this term is meaningless unless this term has some trace meaning on the boundary. So this definition of weak solution is the best possible approximation, from my point of view, of the distributional solution. And this is what one usually does when on combine two-wave equation. They combine a single distributional identity. Now, the most difficult part is to prove that weak solutions are unique. To prove that weak solutions are unique, you have to use an Helmholtz type decomposition, which is sometimes tricky and is untrivial. But this is the technical part of the paper. Now, by using this, you get that the problem is well posed in the Hadamard sense, so you generate a strongly continuous group, which I'm gonna call L of T. Now, let's go to the Eulerian problem. In the Eulerian problem, you have the Eulerian problem, the constrained Eulerian problem, you have the phase space and the solution space, which are in this sense. Also in this case, when you are in X2, you have almost you can define almost everywhere for solution, which is strong solution. And also in this case, you have weak solution, which are defined by two identities. That there are three equations, so you are combining two equations inside the second identity. Also in this case, if P and the divergence of V have some trace sense, you can say that this triple P, vectorial V, and V is a weak solution if and only if is a distributional solution of the equation. No, let's go on. Now, the initial value problem for the Eulerian model is this one, and this denotes the corresponding initial value problem. Oh, also in this case, the constrained Eulerian problem is a particular case of the Eulerian problem. So if you start with the constraint, the constraint will remain forever and ever. Also in this case, we prove that weak solutions are unique. What is strange for this proof of the uniqueness is that to prove the uniqueness of weak solution of the Eulerian model, you have to take the difference, and the difference of two solutions are actually, after integration, a solution of the Lagrangian problem. So it's untrivial to prove directly uniqueness for the Eulerian problem. After you have uniqueness, you prove that also to the Eulerian model, also for the Eulerian model, you have Hadamard well-posedness. So you generate a strongly continuous group on the phase space, you have regularity, and the same conclusion apply to the constrained Eulerian model. So you have well-posedness for 3 plus problems and 2 constrained versions of the same problem. Now, relation among problems. Relations are not so trivial as they appear. So you have to introduce some quotient space. These spaces are spaces for the potential problem. There are U, V, UT, and VT. So these spaces they have 4 components. So you have to make the quotient with, which means this factor means that solution U is constant in space. So C. And the same for the constraint problem. And you have to consider quotient groups. So you have to make the projection. And you denote the quotient group by the potential group and the constrained potential group. No, the theorems say that the groups the potential group and the Eulerian group are similar. Are similar means there is an isomorphism, so you can pass from one problem to the other. But in this isomorphism, U and derivative, they are mixed in the appropriate way. And the constrained groups of the potential problem and of the Eulerian problem are similar. And they are similar with the Lagrangian group. So the Lagrangian group is related to the constrained Eulerian and potential problem. This result has, from my point of view, interesting consequence for the relation between weak solution of the different problems. Now, to give this, we have to introduce several fresh spaces. This is the space of weak solution of potential problem, of the Eulerian problem, of the Lagrangian problem, and these two are the space of solution of the constrained problem. You have to take into account the quotient space. In this way, you have to make a quotient with respect to space and time, so up to functions which are constant in space and time. And then the main theorem says that this formula, which is usually used in theoretical acoustics to introduce the velocity potential and to motivate the potential problem, establish a bijective isomorphism between this space, which behaves in good way in concerning regularity. And this fact is trivial, is easy when n is greater or equal than 2, is untrivial when you look at weak solution, because the isomorphism is not automatic. In this isomorphism, weak solution don't automatically translate into weak solution. Now, there are also bijective isomorphism between the space, the quotient space with respect to the constraint problem, the Eulerian problem. In this case, you don't have to take quotient, and the Lagrangian problem. Now, the isomorphism are induced by this formula. This is the explanation, the mathematically rigorous proof on what they usually do to introduce the quotient problem. How much time do I have? I finished.
3 minutes.
I don't need 3 minutes. I just need 1 minute. Okay. What is the overall conclusion? The overall conclusion is that in the potential problem, there are some strange solutions which appear. Okay, this strange solution disappear when you consider just the constrained problem. And the constrained problem is strongly related to the Lagrangian model. So, this in some sense is a motivation of the fact that is a good idea to consider the constrained potential problem and the constrained Eulerian problem. And they are more or less equivalent up to this isomorphism. Okay? That's it. Thank you very much for your attention.
Thank you very much for your very challenging presentation and interesting problem, really. Questions?
Oh, by the way,
is it simply connected?
yeah, I said at the beginning. If it's not, they don't write, the physicists. Of course. Of course, it is simply connected. Otherwise, it doesn't work. Because you are not able to build the isomorphisms.
In fact, so basically, from the very beginning, you can replace R and V by some greater.
Yeah, but the problem is that when you replace A, you get U, which depends on U. Is the U dependence which is hidden, because to prove the isomorphism, what you do, you prove that the only solution of the equation are constant in space and time. If you don't take into account that they are solution of the potential problem, you can have also, for example, let's speak about V, the Eulerian problem. Vt depends on some unknown function of t, which is a constant in space, but which is the dependence of this V? In time. It works, actually. It was not clear to me, at least, that, and it was not clear to many people that is automatic. Is automatic. You can go on freely.
Yeah, that's what I was. I mean, what seems to be natural, but it's not natural.
Yeah, but you know what happens? That in the paper by Baylor-Rosenkrantz, what they did, they do the automatic replacement, they did small mistakes. So the operator is not well defined. if you just forget the dependence of the constant. And this was a problem at the beginning because we were not able to understand why we had problems. Now everything is
so basically, if you put it in the gradient form from the very beginning, there's something hidden.
Yeah, there's something hidden.
Okay,
yeah.
Okay.
And why to put in the vectorial form? Because in this form, people which likes nonlinear problem can add terms, nonlinear terms. If you try to add nonlinear terms in the potential problem, you get something meaningless. For example, you can write u equals 0 at the boundary, which is meaningless because it's a potential.
Yeah, of course. Yeah. That's great. That was my, when I saw the potential formulation, I was a little bit surprised because you go from Neumann to Dirichlet boundary condition, basically.
Yeah.
I mean, from the normal component to the whole function prescribed at the boundary, right?
Yeah.
Okay.
I don't understand why you said that when he talks about domain is not simply connected.
Because you cannot integrate.
But you can extend it to in a certain sense, to domain non simply connected.
You have the conditioner at the boundary, so you cannot extend the domain. You mean you extend the function?
No, Hugo.
Non ho capito.
If you have a domain that is not simply, so you have a ball inside your domain.
Yeah.
So can you treat that?
I think yes.
No, I cannot.
No?
I cannot.
Okay. Are you sure?
I don't know. I didn't try.
I don't see why. Okay. It's complicated. Yeah, it's just, I think, becomes technical, but because the main point is done here, I think, but I don't
If you are able to treat this case, I will be interested.
if I was 20 years younger, I will do it.
Yeah.
I will propose it to you.
Yeah.
Thank you. Other questions? No. Thank you very much again.
Come?
Professor Fragnelli, and we talk about degenerate wave equations with the drift term, new results, and stabilization.
Thank you very much. So thank you very much to the organizers, in particular to Daniele for the local organization. I am very happy to be here. This is the first time in Varese, so thank you very much. And I am happy to celebrate Vicenzio. So in my talk, I will present new results on the degenerate wave equation. In particular, we will put our attention on a stabilization problem. The prototype that we have in mind is the following one, where t is the time, x is the space variable, and it belongs to a bounded interval of r. For simplicity, we can consider 0, 1. Then we consider at 0 a Dirichlet boundary condition. At 1, we consider this condition. And then we have a drift term. ERB can degenerate at 0. And the equation is degenerate since here we have this term. Here we have the power x to alpha. Alpha is strictly positive, so the term degenerate at 0. And we assume that alpha is strictly less than 2. Then we assume that beta is a constant and eta is a suitable weight function. The reason why we consider this equation is the following. It is well known that the linear theory for waves in a string of length L under tension capital T leads to an equation of this type where u is the vertical displacement of the string at the position x and time t, rho is the density, the mass density, and capital T is the tension. So if we assume that capital T is independent of T, and if we divide this equation by rho, then this equation can be rewritten as an equation of this type where A and B are the following two functions. So if rho is very, very large at a point, say at x equal to 0, the equation degenerates in the sense that we can assume that A at 0 is equal to 0. So we consider this general equation. And we put our attention on the stability problem. That is, we want to find conditions such that the energy associated to the problem goes to 0 if t goes to plus infinity. Before going on, let me frame the problem in the reference bibliography. So if we have an ordinary differential equation or system of ordinary differential equation, then the asymptotic stability was studied in this paper if f is linear or nonlinear and the damping is non-negative. If we consider a hyperbolic partial differential equation, then the asymptotic stability is studied in this paper if f is 0 or nonlinear with a linear growth or genetic, but the damping in this case is strictly positive. Then there are a lot of other results for the stability when the damping is integrally positive or on-off, positive, negative, distributed or localized with a delay. But in all these papers, the equation is always non-degenerate, since here we have the Laplacian. The first result that we have when the equation is degenerate but in divergence form is due to Alabok and Narsen Logering in this paper, where they assume that A is a general function that is 0 at 0, and at 1 they consider this condition, which is similar to our condition. In particular, I recall you that here we have this weight. So this is the first time that an equation in non-divergence form is considered. And the assumption that we made on A and B are the following. So on A we assume that it has this regularity and there exists a constant Ka such that this condition is satisfied. If this constant is less than 1, then we say that A is weakly degenerate, so we can think to the power x to alpha with alpha strictly less than 1. If the constant is greater or equal than 1 but strictly less than 2, then A is said strongly degenerate, so we can think to the power with alpha with exponent greater than 1 and less than 2. On B, we assume that B is continuous and B over A is integrable. The assumption that we made on A are the same assumption made in the paper with the paper of Alabok, Narsa and Logering. So now some remarks on this assumption. So if A is a weakly degenerate, this condition is clearly satisfied, since if we think to the power, then we have that 1 over x to alpha, if alpha is strictly less than 1, is integrable. So B can degenerate or not. If A is strongly degenerate, we have that 1 over A is not integrable. So if we want that this condition is satisfied, B has to degenerate at 0. For example, if we have two powers, x to k and x to h, then this condition is satisfied if the exponent of B is strictly greater than the exponent of A minus 1. So if A is weakly degenerate, this term is negative, so this condition is clearly satisfied. So it is well known that to study a problem in non-divergence form is more difficult than to study a problem in divergence form, since if we have a problem in divergence form, we can use variational tools directly. In this case, if we have a problem in non-divergence form, this is not possible. So the idea is to rewrite the problem, the operator, in non-divergence form as an operator in divergence form, introducing these two weights. But so we can apply the variational tools, but we have to pay a price, and the price is that we cannot work in the usual Hilbert spaces. Here we have to introduce a new Hilbert space, for example L2 1 over sigma, so we have to take into account the degenerate function and these other two Hilbert spaces. Okay, so now we introduce the following product space with this inner product, and we consider the following operator matrix with this domain. So here we have the other condition in 1. Then we can prove that the operator A is non-positive and generates a strongly continuous semigroup. And to prove this, actually it is sufficient to require that A is continuous and this function is non-decreasing in a neighborhood of 0. Actually, if A is weakly or strongly degenerate, this condition is satisfied on the whole domain 0, 1. Okay? And thanks to semigroup technique, we can prove the following existence theorem. So we have a unique solution of the original problem, and if the initial data is more regular, then the solution is classical. Now we have to introduce the energy associated to the problem. And a good definition of the energy is the following one, where here we have the two weights, so we have to consider the degenerate function A, and we have this term. Then we can prove that under the basic assumption on A, that the energy is non-increasing. In particular, we have that the derivative of the energy is minus the derivative of u with respect to t to 2. Then we can prove the following stability result. So if we assume that A is weakly or strongly degenerate, B over A is integrable, and this technical assumption, so here we need that the constant Ka is strictly less than 2. Moreover, we had to add this technical assumption only if the constant is strictly less than 1. Then we can prove that the energy goes to 0 exponentially. And the reason why we require this technical assumption only in this case is since thanks to the fact that this function is increasing, we can bound this term, this function with this term. And so this condition is always satisfied if the constant is less or equal than 1. Just an idea how to prove this theorem. So the idea is to use this lemma that we can find, for example, in the book of Komornik. And according to this result, if the energy is non-increasing, as in our case, and if this estimate holds, then the energy goes to 0 according to this law. So we need to prove this estimate. And to do this, it is important the following are the Poincare inequality. Thanks to this inequality, we have that these three norms are equivalent. Then we prove that the following variational problem has a unique solution. This solution satisfies these two estimates, is more regular, and solves this problem. Now, if we apply this theorem with the lambda equal to u at t and position 1, we can prove that the solution of the problem satisfies this estimate. And thanks to this fact, we have that the integral of the energy is less or equal than the energy plus this term. Now, if we move this integral to the left, and if we choose delta such that the coefficient in front of the integral is positive, we have exactly the estimate that we need. So we have that the energy goes to 0 exponentially. Now we can also consider this term where here we have a singular term. Here the function d is 0 at 0 and the lambda is a constant. We can assume on A and B the same assumption as before. On D we assume that this function is again non-decreasing, and on this constant we require that the sum is less or equal than 2. Okay, so it is stronger than the previous one. The energy that we consider in this case is the following one, where we have this term, and the idea is to estimate this term in some way. In particular, we prove the following Hardy-Poincaré inequality, and if we assume that lambda is strictly less than the inverse of the best constant in this inequality, we can prove the existence theorem, and we can prove that again the energy is non-increasing. So now if we assume we are able to prove that the problem with the singular term is asymptotically stable, assuming the following. So again, D is weakly or strongly degenerate, lambda is strictly less than the inverse of the best constant. Then if A is weakly or strongly degenerate with the constant equal to 1, then we have two different assumptions. They depends on the constant lambda. If A is strongly degenerate with the constant strictly greater than 1, then we have the same technical assumption as before, plus this other technical assumption. Now we consider another problem where here we have a nonlinear term. Rho, the function rho is a non-decreasing continuous, rho at 0 is 0, and there exists two constant and a function g such that these conditions are satisfied. For example, as g we can consider these two functions. For the energy, we consider the same energy that we have for the first problem. And in this case, we can prove that the derivative of the energy is given by minus ut times rho at the derivative of u with respect to t. And actually, to prove these results, it is sufficient to require the basic assumption on A, and on rho, it is sufficient to require that rho is continuous, non-decreasing, and rho at 0 is 0. Now, in order to prove the asymptotic stability for this kind of problem, we cannot use the same lemma that we have found in the book of Komornik, but we have the idea is to use a result of Alabo. And in order to give you this result, I have to introduce some functions. So we consider the function capital H, which is the following one, where g is the function that we have in our assumption, h hat, and capital F in this way. Then we can prove that the function h and its derivative at 0 are 0, f is strictly increasing, invertible, and its inverse is differentiable. Then, if we choose gamma greater than this term, we can define this other function, which is the inverse of f at s over 2 gamma. This function is bounded, non-negative, strictly increasing, and C1. Then this is the last function that we have to introduce, psi 0. And thanks to this function, we can prove that this limit goes to 0 since this term goes to plus infinity if t goes to plus infinity. Then the result of Falabo is the following one. So again, if the energy is non-increasing and the energy satisfies this equality, then the energy goes to 0 according to this law. So now we have to prove an inequality of this type, okay? And actually we are able, under the previous assumption, that this term can be estimated by the energy plus this other term. Again, if we move this term to the left and if we choose gamma so that the coefficient is positive, we can prove the estimate that we need. And so we can prove the following stability result. So for example, if G is the following one, then the energy goes to 0 according to this law. If G is this other function, then the energy goes to 0 according to this other law. Now some work in progress. As I told you, the constant is strictly less than 2. This is a technical assumption. Now we are working on the case k greater or equal than 2. We think that using other technique we can able to prove a polynomial stability. And we are also considering a memory term or a delay. Then we are working on the stabilization of the previous problem with a nonlinear term in the equation, or also with the damping in the equation. And we also are considering the case with the nonlinear term in the boundary, but with the singular term in the equation. And starting from a paper of Lian Radulescu, Xu, Yang, Zhao, we are considering the stabilization for the following problem, where A degenerate at 0. The case F equal to 0 is done in this recent paper in collaboration with Alessandro Camassa, who is a PhD student of mine from the University of Bari. And now we are working on this equation with Camassa and Cristina Pignotti from L'Aquila. So that's all. Thank you for your attention. Happy birthday. And one moment, there is another person who is not here. Wait! He wants to celebrate Vincenzo. Il violoncello no.
Thank you very much for the music. I think he's your child.
It's
for sure, yes. Congratulations. And also for your nice talk too. And now there are questions. Are there some questions?
I have one. So you have a condition lambda less than 1 over a best constant, right? Is that known, the best constant, CHP?
Not for the general case.
And so are available estimates on that? Otherwise means lambda small enough, right?
Yes.
Yeah. But
so there are some cases where it is known.
It's explicit.
Yes.
And in general,
no,
are there estimates or not?
No.
So it would be interesting to find estimates on this optimal constant.
Yes.
Thank you.
Other questions? No. Then thank you very much again. Okay, next speaker is Professor Zhang. Here. Talks about double phase problems with competing potentials, concentration and multiplication of ground states. Please.
Thank you very much. Hello everyone. My name is Zhang. I come from Funan University of Technology and Business. First of all, I express my thanks to Professor Cassani and Professor Radulasko for giving me a precious opportunity to give this talk. Also, Professor Cassani and Professor provide many thanks for applying our visa. Thank you very much. Last year, I and my wife visited Vitillaro in Klein-Gordon-wave of university. Professor Radulasko and Teodora provide many care and help. Very touched. Thank you very much. This time is the first talk through English in offline. I remember last time is Professor Pushy birthday online. I have levels. Okay. My talk is a double phase problem with computing potentials, concentration and multiplication of ground states. This work is work with my supervisor, Radulasko, and my wife, Zhang. Okay. In this work, we establish business concentration and multiplicity property of ground states to the portable double phase problem like this. Apply the topological and variational turbos. We study the existence and the positive ground state solution and relation between the number of positive solutions and the topology of a city, where we attain its global minimum and K attain its global maximum. Moreover, we discover the concentration of ground state solutions, the asymptotic convergence and the exponential decay of positive are also explored. Finally, we establish a sufficient condition for the no existence of ground state solutions. Okay, the outline of talk including the four parts. One, we are concerned the follow problem. In the equations, epsilon is a small positive parameter. This is P Laplace and Q Laplace. There is in this term is absorption potential. This is K is a reaction potential. F is a reaction term with subcritical growth. Pico satisfy these regions. Problem like one arises when one look for the standard solution of reaction diffusion system of the form. This term has a range when the range of application in physics and related science such as biophysicals, polymers physics, and chemical reaction decision, and so on. More background we can find in the paper by the curve and the monograph. Also, the paper, the problem one is also motivated by Lammer's model arranging in the mathematical physics. For example, Biot equations. The model like this. In fact, by that Taylor formula, we have this relation, and by approximation, we can obtain problem 1 for p equal to and q equal to 4. Also, we have multi-physics model. For the case of p equal to p equal to q equal to this, in this case, problem 1 becomes the follow classical Schrodinger equations. For these equations, there are more and more interesting work. For example, Professor Yan and Nierberg, Professor Wei Minye and Junchen Wei, Dapello, Fermer, Labinovich, Siglani, and Professor Xuefeng Wang and Professor Yan Hengding, and so on. They consider the existence, concentration, and multiplicity results. For the case bounded domain and Egyptian equal to 1 for problem 1, Gaskin and Wenker consider single change solutions. Professor Mugnai and Professor Papagio Professor Papagio consider the multiplicity for superlaying growth without air condition. For this case, for this problem, Professor Papagio have done many interesting work. For the case of the whole space and epsilon equal 1, Professor Gongbao Li consider the regularity of solutions for the superlaying case. And this work considered asymptotic U power p minus 1 linear. And Giovanni Figueiredo consider critical grace. Very recently, Professor Filippucci make some good work, like multiplicity results, elective energy for critical export, also some metric solutions for critical problem. Okay, when epsilon goes to 0, this problem we call it some classical state. Alves and Figueiredo consider the follow equations with Alberto Pershing potential V. This is only Fu is autonomous. They obtain the multiplicity and the concentration of positive under the condition introduced by Labinovich. This condition like this, and the nonlinear term F has C1 smoothness with superlinear and subcritical grace. They shown the solution. The solutions well concentrated this set M. M is the global maximum point state. later, Abasaro and Professor Repos relaxed the nonlinear retinue condition. That is a continuous condition. They also obtained multiplicity and the concentration results. Elvis and Sandler, they consider the local condition like this modified by Dipilo and the Farmer work. They obtained multiplicity and the concentration. Okay, our motivation. We would like to emphasize that in all the work mentioned above, the author focused only on the absorption potential wave for the double phase problem. In other words, the multiplicity and the concentration results depend on only on the property of potential wave. Moreover, the problem is autonomous in the reaction. That's why it's quite natural to ask how the appearance of absorption potential wave and reaction potential K will affect the existence, multiplicity and concentration of solutions to problem 1. The main features of this work are as follows. The problem combines the multiple effects generated by two variable potentials. 2. There exists a competition effect between V and K. Because this happens because we have a chance to attract solutions to its mini maximum, while the K wanted to attract solutions to its maximum point. 3. The main concentration phenomena create a bridge between the global maximum point of solution versus the global maximum of the reaction potential and the global maximum of absorption potential. 4. Due to the unbroadness of the domain, the PS sequence do not have the continuous property. Okay, in order to state over results, we start with the follow basic notations V meaning and the set V limit also, and for K max the set K infinity like this. We assume that V and K satisfy the follow conditions: A0, V, K continuous and bounded, also both positive. A1, V meaning less than V infinity, and there is xv in set V. Such that kxv more than or equal to kx for x in large. A2, k max more than k infinity, and there is xk in k, such that vxk less than or equal to vx for or x in large. A3, this condition like this. Note that for the case A1, we can assume that kxv equal to kx max kx on way. Also for case A2, we some way xk equal to mini vx in k. Okay. To describe concentration phenomena of positive ground state solutions, we define two concentration sets related to potential V and K. AV like this, AK like this. And we just assume that the nonlinear term F satisfies the follow hypothesis F1, 2, 3, 4, 5. This condition is a later growth condition. F4 is an AR condition. F is a Nehari condition. Theorem 121. Suppose that A0, A1, and F1 to F5 hold, then for all small epsilon more than 0, we have four conclusions. One is that problem 1 have at least the positive ground state solutions. 2. L epsilon is compact, where L epsilon denotes the set of all positive ground states. Conclusion 3 is a concentration phenomena. That is U epsilon possesses a maximum point x epsilon goes to x0 and line in AV, which implies our concentration. Also, for solutions U epsilon have they follow asymptotic behaviors. Conclusion 4 is decay property, that is exponential decay. Theorem 122. Theorem that A0 and 2, F1 and F5. We replace the AV by AK. We also obtained the similar conclusions. To obtain the multiplicity result of solutions, we recall the LS category definition like this. And we also assume that V the intersection of V and K is not empty, and so we establish the following multiplicity property. Okay, suppose that A0, A1 or A2 and F1, F5 and lambda is not empty. Then for any delta more than 0, there exists epsilon delta more than 0, such that epsilon line in this range problem 1 have listed category positive solutions. Finally, we give the no existence results of ground state solution as follows. And we have theorem 1.4. Assume that A3 and F1, F5 we have this result. Additionally, we also consider double phase problem only with reaction potential, and we also obtained some similar results. Now we introduce the variational framework and preliminary results. In fact, after the change of variable, we can rewrite the problem as the follow equivalent problem. We observe that if U is a solution of problem 4, then Vx, that is U x over epsilon, is a solution of problem 1. So we study problem 4. Okay, for any fixed epsilon, we introduce the follow worker space like this, and we also have the m-binding property, lemon 2.1. Okay, now we define the energy function on phi epsilon and the phrase and derivative. We consider the Nehari manifold like this n epsilon studied by Schrodinger and Weiss. That epsilon like this. By this way, we can define the ground state. Now, consider the functional Egyptian height and restriction Egyptian from S Egyptian to R as follows. Lemon 2.2 come from Schrodinger and Weiss the work. This is the main results of Nehari method. 3. We consider the constant coefficient problem. Now, for any mu and the kappa, we consider the constant coefficient like this, and by Nehari method and the concentrated compactity argument, we can prove this results. Also, we need to establish some comparison results under different mu and kappa. This results will be used. Now it is the proof of many results. Proof theorem 1.1. We first consider the situation A0 and A1. We set V tilt and kappa tilt. It is clear that if U tilt is a solution of the U solves the problem 4. By condition A0 and A1, we have this relationship. This automatic problem is very important for later proof. Step 1, we analyze the PS compactness condition by snipping lemma and energy comparison method. This is result. Step 2, we will prove the existence of positive ground states, and we need to prove this energy relationship and obtain the existence of positive ground states. Step 3, we show compactness of the set of positive ground states. This results. Step 4, we will prove the concentration Fermi for the positive ground state U epsilon the results as follows. Finally, we will study the exponential decay property of solution. The results as follows. Okay, the proof of theorem 1.3. We are going to show the multiplicity of positive solution and study the behavior of their maximum point in relationship. Let U are positive ground problem 7. Now there is a process of growth of proof. Next, we shall use the LS category in theory and the idea benzene ceramic to prove these results. Since Egyptian is not C1 submanifold, we can't directly apply the LS category theorem. Fortunately, we can know the mapping M Egyptian is a homomorphism between Egyptian and S Egyptian. Now we can apply the LS category to functional Egyptian. Okay, this is a process of proof. Another, we also consider double phase problem with local reaction. Thank you very much. Happy birthday to
Thank you very much for your presentation. Questions?
How do you prove non-existence?
Yes.
How do you prove non-existence
Non-existence.
of solutions? No?
The non-existence.
No, doesn't matter. Doesn't matter. Thank you.
Okay. Okay. Then
Thank
you again.
Okay.
Good afternoon. I think we can start this afternoon session. Our first speaker is Chao Ji from University of Science and Technology, Shanghai. He will speak about multiplicity and concentration results for a magnetic Schrodinger equation with exponential critical growth in R2. Thank you.
Thank you. Okay. It's my great honor to have this chance to give a talk. Thank organizer for your, it's okay. Thank organizer for your hard work. Thank Kasani. Okay. And I'm so happy to meet many new friends and old friends. And the most important words I would like to say, happy birthday, Vincent. You give me much support and help. You're something. Your many mathematics model. I think I learn more something from you. Okay. Today I would like to talk about multiplicity and concentration results for a magnetic Schrodinger equation with exponential critical growth in R2. This is a joint work with Pietro D'Avenia, who is Italian, maybe from Bali. Work for Bali, Bali. And Vincent Radlascu. Okay. This is I don't know which. Okay. This is let's take a look at the magnetic Schrodinger equation like this. Here, Ax is a vector function, which is the magnetic potential, and kernel of A denotes the magnetic field strength. The Schrodinger equation without magnetic field is not suitable for articles with a spin. The physicist Pauli extended the Schrodinger equation and provided a new Pauli equation which can describe the influence of the interaction between the external electromagnetic field and the and the spin. We would like to look for the standing waves like this. This is related to the this equation. This is a complex semilinear elliptic equation. This is the magnetic Schrodinger operator, whose definition like this. Here and here, there the vector function A appears. So if A equals 0, this part equals 0. So it will become the classical Laplacian. Right now, let's recall some results without magnetic field about this equation. The first result is due to Flow and Weinstein. They here in this paper, the potential Vx is global bounded, where the Lyapunov-Schmidt reduction method, they constructed a standing wave which concentrates around a given non-generator critical point of Vx. For the case n equals 1, p equals 3. And after this paper, O extended the results of this paper to high dimension. In this paper, p is bigger than 0, is less than n plus 2 over n minus 2. And in this paper, Wang used the variational methods. Vx is bounded below. They prove the positive ground state which concentrated at the global minimum point of the Vx. Okay. In this paper, Rabinovich provided a global assumption of potential Vx. He used the global variational method to prove the ground state. And Dapino and Filmer gave a local assumption about the potential Vx, they proved the sequence solutions which concentrated on the local minimum point of Vx by introducing a parallelization method. And in this paper, Alves and Figueredo considered multiplicity and concentration results for n-Laplace equation. In this paper, the potential Vx satisfied a global assumption like this, and the nonlinearity satisfied. The nonlinearity has exponential critical growth, and Vx satisfies. Zhang Jianjun and Dodo considered the standing waves involving critical growth of Schrodinger Moser type. In this paper, the potential satisfies a local assumption. They just consider the existence and the concentration of standing waves. They didn't consider the multiplicity of standing waves. Moreover, we can Ding and Tanaka consider the multi-bump solution with depending well potential of this equation. Here, always extending the results of this paper to the quasilinear elliptic equations. For more results, we can check the papers from Ambrosi T. Biang, Ding Yanheng, Peng Shuangjie, Wang Zhiqiang, and so on, and so on. Okay, let's recall some results about Schrodinger equation with magnetic field. The first result is due to Esteban and Lyons. They used the concentration compactness principle and minimization arguments to get the solution for p epsilon. Here epsilon is fixed, is a positive, and n dimension n equals 2 and 3. And Alves, Figueredo, and Furtado, and considered the multiplicity and concentration of non-trivial solutions of Schrodinger equation with magnetic field. In this paper, the potential satisfies a local assumption, and the nonlinearity has subcritical growth. and the Tang Zhongwei considered multi-bump bound states with critical frequency, which means the infimum of Vx equals 0. And as far as I know, this is the first paper who studied the Schrodinger equation with magnetic field, and the linearity has exponential critical growth in R2. They consider the problem in radially subspace, so maybe that it has a compact embedding. Okay, and Radulescu and I considered the multiplicity and concentration of non-trivial solutions of Schrodinger equations with magnetic fields in subcritical case and critical case respectively. In these two papers, the potential Vx satisfies a local assumption. The most importantly is the linearity F is just continuous, not is class C1, so we cannot use Eckland variational principle. That's the difference, and that's a difficulty. We have to use another technique to conquer these difficulties. And Ambrosio systematically fractional Schrodinger equations with magnetic field. He also made some research about fractional Kirchhoff equations with magnetic field, fractional Chukada Poisson systems with magnetic field. Okay. From the papers I mentioned before, we have a natural problem when n equals 2 and the linearity has exponential critical growth. What about the multiplicity and the concentration of non-trivial solutions to problem P epsilon when the potential V of x satisfies a local assumption, which is due to Depino and Fermat, or a global assumption due to Rabinovich? What about the multi-bump solutions for the magnetic Schrodinger equation with the depending well potential? Okay, we know it's well known that H1 of Rn is continuously embedded into LQ of Rn. Here Q is bigger than or equal to 2, is less than or equal to 2 star. Here 2 star is a critical point, a critical exponent. Okay, if n is bigger than or equal to 3, like equals this. So where the maximum growth, the absolute value of u to power 2 star is called critical Sobolev space growth. But for n equals 2, H1 of R2 is not embedded into L infinity of R2. So there is no best target LQ space for the embedding. What's the best target space for the embedding? It's to look for a function GS with the maximum growth such that supremum of this integral is finite. So from the book, we know that the optimum embedding of H1 of R2 into a certain Olli space. To be more precise, the maximum growth is of exponential type. What's the Olli space? I just mentioned it. What's Olli space? It's a generation of LP space and Sobolev space. In LP space, this convex function is very important. If we replace this convex function by another general convex function, you can get the Olli space. Okay, let's move on. Important inequality for our study, which is the Schrodinger-Moser inequality. Okay, if alpha is bigger than 0 and u belongs to H1 of R2, then this integral is finite. But for infinite pi's alpha u, maybe this integral is not uniformly bounded. Moreover, if L2 normal of gradient u is less than or equal to 1, L2 normal of u is bounded, alpha is bigger than 0 is less than 4 pi, then there exists a constant c, which depends only on m and alpha, such that this integral is uniformly bounded. Okay. It's a position to give our first result. Assume we satisfy the following assumptions. Informum of Vx equals V0, which is positive. There exists a bounded open site lambda such that infimum of Vx in lambda is less than minimum of Vx on partial lambda. This is a local assumption about potential Vx, so we don't know the information about Vx at infinity. Okay, the magnetic vector potential A is Holder continuous with exponent alpha. Alpha is bigger than 0, is less than or equal to 1. Actually, when after this work we further our research, we found this condition can be weakened. Maybe yes, A is continuous is enough. It's not okay. Okay, f is a C1 function because Sobolev space at A1 its topology is trivial. We cannot find some multi-solutions. We would like to find some solutions on inherent manifold. Maybe more precisely, we would like to find some multi-solutions on some side and on inherent manifold in inherent manifold. So f is C1, so inherent manifold is C1. So and this assumption means the linearity f has exponential critical growth. Okay, this is a Ambrosini-Ramanovich condition, which is help to prove the boundedness of the PS sequence. Okay, this condition, this assumption is more complex. Cp is bigger than two numbers. Cp is bigger than this number. We can show that the positive ground state of limit equation is radially symmetric. So it means positive ground state is decays exponentially at infinity with its gradient. Moreover, we can show positive ground state is C2 and L infinity. Cp is bigger than this number. We can show the ground state energy of limit equation is less than one number. So the norm of the PS sequence for limit equation is less than or equal to 1. So we can use the Morse-Schrodinger equality. Okay, maybe later I'll show you why we do have to assume this condition. Okay, the first result is assume that we satisfy this condition that I mentioned before. So for any delta is bigger than 0, such that this site is contained delta. For if epsilon is small enough, so problem P epsilon has at least this category non-trivial solutions. Okay. Moreover, if eta epsilon n is the global maximum point of the modulus of U epsilon n, so we of eta epsilon n go to the V0, which is a local minimum of Vx in delta. Okay, we consider this in equivalent problem. So in order to study this problem, we meet some difficulties. For example, we will work for a new Sobolev space, which is a magnetic Sobolev space. So we need to know some knowledge about this space. And because we work in unbounded domain, so the compactness is lost. So we need to conquer this difficulty. and because the magnetic field appears and the linearity f has an exponential critical growth, so some estimates are different and dedicated. So this is the workspace we will work for. Okay, because we know the embedding results about this stability space, but for this we don't know, and there is no relationship between these two stability space. But we have this: if A belongs to L local 2, so the diamagnetic inequality holds. Because of this inequality, we have the normal stability of embedding. And in order to solve the loss of the compactness, we will use the penalization method due to dipinel and film, like this. And okay, we will work for this modified problem. So this the function of this equation corresponding to satisfies the PS condition under some level. Okay, we will, as I said before, we will look for the multi solutions. So we will work for we will work on inherent manifolds because the topology is richer than stability space. So the function of J epsilon restricted to N epsilon satisfies the PSD condition at any level D. D is less than this number. Because D is less than this number, the normal of PS sequence is less than or equal to 1. So we can use the Schrodinger inequality. Okay, now we have to say the solutions G epsilon restricted to N epsilon are the solutions functional G epsilon on in HA1. Okay, so because from this assumptions we have G epsilon of UN goes to D, and because of the Lagrange multiply principle, there exists lambda n such that this holds. From the conditions F1 to F4, we can prove T epsilon prime of UN act on UN goes to a positive constant. So lambda n goes to 0. But we don't know, even lambda n goes to 0, but we don't know if this term goes to 0, because if the norm of T epsilon of prime of UN goes to infinity, maybe this goes to maybe a constant not equal 0. So because of condition F5, we have the boundedness of the normal of T epsilon prime of UN. So F5 is important. Okay. We will work for this space, this subset, and we have the following diagram. M construct a continuous function from M to this side. Moreover, construct a continuous function from this side to M delta. If composite map this is homotopolically equivalent to the embedding this, then the topology of this site is richer than topology of this site. In our case, the category of this site is bigger than or equal to the category of this site. So after this, in this pages, we show how to construct these two maps. Okay. I just say this lemma. This lemma shows that this set is not empty. Is important, and in order to prove this limited holds uniformly in Y belongs to M. So we need to prove this limit holds. So in order to prove this limit, we need A is the hold continuous with exponent alpha. After this paper, we find another proof of this lemma. We found A is continuous is enough. So this assumption can be weakened. Okay. Finally, we will show the solutions of the multiplied problems, other solutions of the original problems. So here we will use we have to give L infinity estimates for the solutions. So here we use the Moser's iteration. And using the Moser's iteration, we have this inequality. But if we have to show Vn, L infinity normal of Vn in this subset is small enough for n uniformly. So we need the modulus of Vn has a convergent subsequence in H1 of R to R. So in order to prove this compact result, we need this limit because this CV0 is ground state energy of the limit equation. Okay, because this limit, ground state, the positive ground state of limit equation is concentrated at a point. So because the modulus of Un has a similar shape with positive ground state of the limit equation. So we can show this compact result. Actually, here we use the concentration compactness principle due to length. Okay, the clock. Okay, the second result, we extended this result, the result due to of this paper. This paper considers the multiplicity and the concentration of n-Laplace equation, and here the potential Vx satisfies a global assumption like this. In this paper, we just assume A is continuous. Okay. This is the Ambrosity-Rabinovich condition, and from F4 we have the similar result. For example, the the positive ground state of the limit equation is radially symmetric, and which decays exponentially at infinity with its gradient, which is C2 intersects L infinity and so on. And the ground state energy of the limit equation is less than some numbers. So PS equals of limit equation is less than or equal to 1. So we can use the Moser-Schrodinger inequality. There's a similar action effects. Okay. Here, in order to conquer the loss of the compactness, we will compare the energy of the limit equation and the energy of our problem to conquer the loss of the compactness. So this lemma is very important. This lemma is kind of Breeze-Label type results. In Elvis and Figueroa paper, they also need this lemma. In their paper, they assume that L square is this limit is less than 1/64. L square is 1/64. So by some dedicated estimates, we just need this. So even for even for Schrodinger equation without magnetic, we also is also holds. Okay, the first result is we can get a ground state solution. We can get a ground state solution, and we also can get a multiplicity, and moreover, we can give dedicated estimates if A is a class C1, so we can prove the solution is C1. So if the solution is a class C1, so we can use a Kato's inequality and the sub-solutions estimates, so we can get the modulus of U epsilon n decays, exponentially decays at infinity. Okay, the final result is related to nonlinear magnetic Schrodinger equation with depending Welt potential. Okay. Here omega equals interior v minus 1 of 0 is non-empty bounded open side with smooth boundary partial omega. Omega can be decomposed in k connected components omega 1, omega 2, omega k. Okay, our just to show a result. Our result is if this condition holds for any non-empty subset gamma of 1 to until 2k, if lambda is big enough, we can get a non-trivial solution U lambda. Moreover, U lambda converges strongly in this Sobolev space to a function U. Ux equals 0 if x does not belong to omega gamma, and the restriction U on omega g is a least energy solution of this equation. In order to consider this equation, we also have some difficulties. For example, the loss of compactness. We will use the penalization method due to dependence of the FIMO. Because in this paper, we would like to find some special solution, not just a solution. We would like to find some multi-bump solutions. So we will use a precise analysis of the deformation flow on some special subsize. Okay, that's all of my talk. And thank you very much, and have first visit. Thank you.
Thank you for your talk. Are there questions or comments? Okay, if not, we thank again the speaker.
Thank you very much.
Thank you. So the next speaker is Schiera from Istituto Superior Tecnico, Università de Lisboa. She will speak about spectral optimization for weighted anisotropic problems with Robin condition.
Okay, thank you very much. So first of all, thanks for the introduction, and of course I wish to thank the organizers for this great opportunity. It's for me an honor to be here, to be part of this conference, but actually it's also a great pleasure for me because for me everything started here, and so it's like coming back home. So especially I want to thank Daniele. And okay, so today I'm going to present some results I got in collaboration with Benedetta Pellacci and Giovanni Pisante, and of course you can find everything on the posted on archive. Okay, so I would like to start with a bit of motivation, just to contextualize a bit our results. So I will start with a very well-known problem, the diffusive logistic equation, which is a model for population dispersal. How does it work? If U represents the population density of a species which inhabits a region omega, omega is a bounded domain, will always be a bounded domain. Then this represents a population which moves via a random walk process, which is modeled by the Laplace operator, with a diffusion rate D, which will play an important role. C describes the effect of crowding, so it is in front of the quadratic term. Then the weight m is crucial and will be crucial in our analysis, is basically represents the allocation of resources in the region. So if m is positive, then you have a favorable area in the region omega. If m is negative, then you have an unfavorable region. And for us, the weight m will always belong to this class here. So they are L infinity functions bounded between these two constants minus beta and 1. And we are assuming that m changes sign. So the region in which m is positive has a positive measure. And also we are assuming that this integral is negative, and also we have, let's say, a mass constraint. Okay, and the last thing which is important is that we are considering Robin boundary conditions. So if this constant k is equal to 0, you recover Neumann boundary conditions. And this represents a domain in which the frontier acts as a barrier. Whereas if k is equal to plus infinity, you recover Dirichlet boundary conditions. So the population dies immediately when gets off the domain. And of course, if k is in the between, you have something which is a combination of these two extreme situations. Okay, so what is known for this problem? It is known that the corresponding steady state problem plays a crucial role in understanding whether the population persists or if it goes to extinction. So it turns out that the corresponding steady state problem has a unique positive solution, which is an attractor for solutions of the diffusive logistic equation, provided that the diffusion rate d is below this value here. Whereas if d is above this value, then the trivial solution is an attractor. So in this case, you have extinction of the population, whereas in the first case, you have a persistence. So it is clearly of interest to understand better this value 1 over lambda of m. And lambda of m turns out to be the positive principal eigenvalue of the corresponding, say, linearized problem, which is in this case simply the Laplace operator with a Robin boundary condition and a weight m. So just to recall you briefly what is the principal eigenvalue and really the main properties, you can, in this case, you can write it in a variational way. It can be characterized in this way. It is an infimum of this value with a mass constraint. And you can prove that actually this principal eigenvalue exists. So you have a principal eigenfunction which is positive, or at least you can choose the sign. It has a strict sign, so you can choose it positive. And there is only one principal eigenfunction up to a multiplicative constant. And it is the only positive eigenfunction. And also it is, this is the first eigenvalue. Okay, so just to sum up, we are interested in this problem, and we find out that this value is crucial to understand persistence or extinction of the population. And so it is clearly of interest to minimize this lambda of m with respect to the weight m, because if lambda is small, then this value becomes big, and so you have persistence for larger values of the rate diffusion d. So from now on, our goal is to understand this minimization problem. Okay, I put a slide with some very, very partial bibliography because it's impossible to cite everyone, of course. I would like just to say a couple of words more on some papers which were of inspiration to us. So this paper by Cantrell and Cosner, there is a series of papers by Cantrell and Cosner, Liu Yanagi, Intermulle Carl Loren, Lambole Lorena Di Privat, in which they completely analyze the one-dimensional case, and I will say more on this later because it's really crucial for our analysis. And also they prove some, I would say, surprising results in the higher dimensional case. And also would like to mention that you can consider other different diffusions, and this is actually what we are going to do. We are going to substitute the Laplace operator with a different operator. Okay, so What is known still for the Laplace operator? It is known that best weights are of bang-bang type. So what it means that a weight is of bang-bang type? It means that it is a piecewise function which attains its maximum and minimum value. I recall you that M is in the class of weights which are bounded between 1 and minus beta, so it attains these two values. And now that you know this fact, okay, so it is also important to recall that the corresponding eigenfunction, if you take the super level set of this eigenfunction, you recover this D here. Okay, so now that you have this property, the minimization of lambda with respect to M can be translated into the minimization with respect to this set D. So now you have the problem of understanding which are the best subsets D of omega, such that lambda is minimum. Okay, in the one-dimensional case, as I said, the minimization problem is completely solved. So on the left side, you have the Neumann case. So the best weights are this one and the symmetric one. So the one which is first minus beta and then here is equal to 1. They are both optimal. Whereas in the Dirichlet case, the best set D is centered in 1/2. So this is, okay, omega in this case is 0, 1. And the best weight is symmetric in this way. And if you have Robin boundary conditions, you have something in the between in the sense that there exists a critical K star, such that if K is below this K star, then you are in the Neumann situation. If K is above K star, then you are in the Dirichlet situation. And if K is equal to K star, then every set D is optimal. Okay, so as I said, our goal was to try to perform basically the same analysis, but with a different kind of operators. And the idea was to consider an anisotropic P Laplace operator in order to model a population which disperse with different probabilities depending on the direction. Okay, so the anisotropic P Laplace operator is an extension of the P Laplace operator. So you see this H substitute the modulus, the norm. Okay. Of course, you have to modify a bit the corresponding reaction diffusion equation because first of all you need some sort of homogeneity. So you have to put this exponent P here, and the Q is a positive exponent. Doesn't matter. And the boundary conditions change accordingly, and this is a consequence of integration by part. So you get it is exactly the same equation, but translated into this new setting of the anisotropic P Laplace operator. Of course, it is crucial to understand what is H and the properties of H. Okay, so the idea is to take almost a norm. So H is positive, it is equal to 0 only in 0. Let's say the corresponding ball is uniformly convex. But the crucial thing is that we are assuming that it is positively homogeneous, so it is not homogeneous in the sense that this property also only for T positive, not for any T. So in particular, H is not assumed to be even, so it is not a norm. And it is crucial, especially in the one-dimensional case, and I will say a bit more on this in the next slide. I just wanted here to cite a bit of literature on this operator. I would say that maybe the best way to start is this paper by Belloni, Ferrone, and Cavol. And also would like to cite to say that there are a lot of other, let's say, anisotropic operators that you can consider, and we didn't treat these kind of operators, but of course it would be of interest to understand what happens for different kind of anisotropies, if you can recover more or less the same results or not. Okay, so a couple more of remarks. As I said before, if H is let's say the modulus, then you recover the P Laplace operator. We are not assuming H to be even, and this is crucial in the dimension 1, because if H is even, under all these assumptions, H is forced to be a multiple of the modulus. So you basically don't see any kind of anisotropy. And this lack of symmetry is crucial also from a mathematical point of view, in the sense that in this case, you don't have just one principal eigenvalue, as in the Laplace or the P-Laplace case, but you have two positive principal eigenvalues. One is the lambda plus, which takes care of the positive eigenfunction. So there is a lambda plus which has a positive eigenfunction correlated to it, and it can be obtained through minimization on the cone of the positive functions. And you have a corresponding lambda minus for the negative eigenfunction. So you have two positive principal eigenvalues, and of course the first question is which one we have to minimize. And to study everything in this new context. And I would like just to mention that this thing of having two positive principal eigenvalues is a phenomenon which occurs also in the case of fully nonlinear operators. If you are familiar with Pucci operators, it's exactly the same phenomenon. Okay, so as I said, the first thing to understand is which one we have to minimize from let's say, physical point of view. The natural choice is lambda plus, because we proved that this is the right threshold for existence of positive solutions for the corresponding reaction diffusion equation, whereas lambda minus will be the threshold for negative solutions. So since U in our, let's say, model is the density of the population, it is completely natural to understand the lambda plus. But from a mathematical point of view, also the lambda minus is interesting, and we also treated this situation. And you can still prove that optimal weights are of band type. And the most surprising result is in the one-dimensional case. And this was actually our main goal, to try to understand what happens in the one-dimensional case, because I recall that in higher dimension, also for the Laplace case, there are a lot of open questions, whereas in the one-dimensional case, the situation is well known. So we wanted to understand if this anisotropy really plays a role or not when you try to understand this minimization problem. And it turns out that, of course, it makes a difference, and this is our main result. So we proved which is the best optimal set in the case k is equal to 0, so in the Neumann case and in the Dirichlet case. And now, yes, I have time. I would like to say a couple of words on both these results, and not just what we proved, but also a little bit of the idea of the proof. So this is the Neumann case. In the Laplace case, these two weights were both optimal. Here, if A is bigger than B, then you are in the first situation. So the best weight is this one and not this one. And if A is less than B, then you have the opposite situation. So the anisotropy in the Neumann case tells you which one is the best, is the best weight. And the idea of the proof is based on rearrangements. So the thing is to understand which rearrangement works better. And in this case, you have to take the monotone decreasing or increasing rearrangement. So this is the formal definition, but okay, of course, as every time when you are dealing with rearrangement, the crucial property is that superlevel set of U and of the rearrangement of U have the same measure. And this is a picture, just a qualitative picture to give an idea of what's going on. So you have, if you have a function like this, you have something which looks like that. And okay, it was known, okay, the main references here is this book by Cavol, not just for this rearrangement, but in general for rearrangements, and this paper by Berestiki-Lachamberbert. So it was known that you have an Hardy-Littlewood inequality, so U times V, the integral of U times V is below the integral of U star V star. And also it is crucial to have a Polya inequality, so to understand the integral of U prime and the integral of U star prime. It was known for the case H equal to the modulus. So what we did is to extend it to the anisotropic, to this anisotropic situation, and the proof of this is really constructive, I would say. And the important thing is that you also have information in the equality case. So if equality holds here, then U is monotone. And now the idea of the proof is that first of all, you want, okay, you take phi to be the optimal positive eigenfunction, and you want to show that it is monotone. So lambda plus can be written as an infimum over a suitable set of positive functions of a Rayleigh quotient. And now you take lambda plus is the optimizer, okay? Phi is the optimal positive eigenfunction, so you have equality here. And then using these two inequalities I already presented, you get that the phi star, let's say the rearrangement, is below this Rayleigh quotient, but lambda plus is the infimum over all possible weights m. So you have this chain of inequalities, which tells you that you have actually an equality. And so now you use the equality case in the Polya inequality, and you prove that phi is monotone. Okay, and now you have to prove that actually the best one, for instance, in the case A bigger than B, the best one is the one which is, let's say, with maximum value close to the 0. So assume by contradiction that phi is increasing, and then you have to choose a suitable rescaling of phi, make some computations, and okay, I don't want to enter too much into details, but it is really a matter of computations to see that if B is below A, then this gives you a contradiction. Okay, so phi cannot be increasing, so it must be decreasing, and you conclude. For the Dirichlet case, what we proved, I recall that in the Laplace case, the best D was exactly symmetric, so it was centered in 1/2. Here you have an exact representation, so we know exactly which is D1 and D2. And it turns out that depending on the values of A, B, this set can be closer to 1 or closer to 0. So if A is above B, then it is closer to 1 or it is closer to 0. And here the proof is still choosing the right rearrangement. And here the right rearrangement is the anisotropic rearrangement, which is a sort of anisotropic version of the Schwarz symmetrization rearrangement. Okay, this is the formal definition. The main reference here is this paper by Van Schaftingen. And okay, the idea is take the same function as above. If you take the symmetric decreasing rearrangement, you expect something like this, so something which is symmetric. But if you take the anisotropic rearrangement, you have something like this. So you weight differently the decreasing part of the rearrangement and the increasing part of the rearrangement, which is completely, I mean, it makes sense if you think about the thing that the anisotropy in this case weights differently the part in which the U prime is positive or negative. So it makes perfectly sense to weight differently also in the rearrangement. And now we need exactly the same inequalities as before, so an Nadelite-Wood inequality, which was already known in this paper by Van Schaftingen. And the crucial thing is the Polya inequality. There is some results in the Van Schaftingen, but only for dimension bigger than 2. And in particular, there are no results for the equality case, which is crucial for our arguments. So what we did is to prove this Polya inequality with of course, the anisotropy H, which plays a role. And the important thing is that if U is C1, which is the case in our situation, and if you don't have, let's say, flat zones, then U is basically equal to its anisotropic rearrangement up to a suitable translation. Okay, and now the idea is more or less the same. So first, actually, since here you need this red condition, so you don't want flat zones. First of all, we proved using increasing and decreasing rearrangement that the optimal phi increases and then decreases. And also using convexity of H, you prove that this monotonicity is strict, so you don't have flat zones. And now you use the anisotropic rearrangement, more or less as before, and you use the equality case, which we proved in the Poglia inequality for the anisotropic setting, and you concluded that the best eigenfunction, it's anisotropic rearrangement, coincides with this anisotropic rearrangement, and so this tells you immediately that that optimal D is of a specific form, as I said before. And now, just to conclude, I would like to say that we also treated the case lambda minus, and you can prove something similar. Everything works more or less in the same way. Of course, there are some modifications to take into account, but I would like just to say that if omega has a center of symmetry, in this case we are in any dimension, and if you are in dimension 1, this hypothesis of symmetry is always satisfied because you have an interval, so there's nothing to assume here. Then the infimum of the lambda plus and the infimum of the lambda minus coincide. Okay, it is important to notice that lambda plus and lambda minus in general do not coincide for a fixed M, and also that these two infimum are not in general attained by the same M. Actually, this is not in general the case, but the infimum is the same value. And we also proved something more in the dimension 1. In dimension 1, and when you're dealing with the Dirichlet or Neumann case, then you can actually say explicitly which are, let's say, the best weight for lambda plus and the best weight for lambda minus, and you see that they are related in this way, so there is a sort of symmetry going on here. And that's all. Thank you very much for your attention.
Thank you, Delia. Thank you very much for your talk. Are there comments or questions? Okay, if not, let's thank again Delia. Our last speaker is Wei-Ping Yan. He will speak about stabilizability for a quasilinear Klein-Gordon-wave system with variable coefficients.
Many thanks to Professor Lascu for invitation me to here for this conference. Happy birthday. And many thanks to Professor Cassini for his organization and the help. It's my honor to come here to give this talk. Okay, my talk name is Stabilizability for quasilinear Klein-Gordon-wave system with variable coefficients. This is joint work with my student is Jun Liu in Guangxi University and Zhang in Wuhan University. Okay, the talk is mainly divided into 4 parts. One is introduction and main result. Second is global work properties for the linear Kelvin-Voigt damping Klein-Gordon-wave system. The third part is construction of approximation solutions. The third part is a proof of a main result. Okay, the stabilization problem is one of the classic problems in control theory. It has been widely studied in many cases of partial differential equation. The stabilization is an action to render a system more stable than its nature with the help of some well-designed feedback laws. Please the work of J.L. Lyons, the 2 papers of him. Okay, where various types of damping were employed as feedback laws to stabilize the elastic system. In general, there are 2 types of damping, that is linear viscous damping and Kelvin-Voigt damping. The first one usually models external friction forces, and another one came from the inner friction of the material of the vibration structures Kelvin-Worley damping is stronger than linear various damping when the global distribute size later only produce external stability and not any level of smoothing property. There's two papers concerning this topic. Okay, I list some papers related to this talk, but I cannot list all of the reference because the limit of the time of talk. Okay, Yu Han considered the following abstract evolution equation like this one. A is an operator. He writes a system as an evolution equation. Okay, this is the second. Last is the domain of the operator A. Then they get the following result. They prove the solution will be decay in a polynomial with rate as this kind of. Okay. Then Amory and Harrison and Robano consider the following Cauchy problem. Okay, I also write it in evolution equation form. So he get the following form. For any k, there belongs to integer. There exists the C such that for any initial data, the solution of above equation starting from initial data satisfies the following energy estimate. So you can see the energy will decay, but not the potential decay is the log decay in time. Bock considered the following Kelvin-Worley damping linear wave equation as the following form. The generator A is given by like a matrix form, with the domain is this form. So energy of it is the following form. Okay, then they get the following form. Let omega belongs to RD be a small C2 domain, assume that the damping term A bigger is non-negative is in L infinite space and is bounded away from 0 on an open set omega, and it satisfies the following conditions. So then for any k there exists a C such that for any initial data belongs to the domain, then they get the energy decay. Like this form is also a log decay in time. Okay. Then we also get the following result. Let omega be a small C3 domain, assume that the A is non-negative, satisfies the following condition. 1, there exists a third bigger than 0 such that the internal of the set omega controls geometrically big omega. And that means all rays of the geometric optics reflecting on the boundary according to laws of geometric optics eventually reach the set omega in infinite time. Then the energy decays polynomially like this, like this form. The energy will decay like this form. Okay. Recently, Liu Zhang considered the following linear equation with local Kelvin-Worley damping. I also write the evolution form. A is the operator defined as that way, and the domain A is in this form. The function B x is assumed to be satisfies this form. Is at this form. Then they get a more condition on B and on conditions A. Okay. Then they get the following result. Suppose the conditions function B is defined as bar and the condition A1 tells then the semigroup ETA A is exponentially stable if damping conditions A satisfies the following condition. The second result is the semigroup ETA is polynomially stable of the order this form if A satisfies A2 condition with A is bigger than 0, smaller than 1. Okay, above result is also on all of above result is a linear equation with damping. So for a nonlinear, especially quasilinear case is field result to our knowledge. So so there is a field works on stabilization of quasilinear equation. The global openness has been established in Ma and Katayama for quasilinear Klein-Gordon-wave system admitted no condition of quasilinear terms. Those are two papers. So, okay, for quasilinear wave equation, if the quasilinear term satisfy no condition, then we can use Klein-Man's energy estimate to get the global existence. But if the quasilinear term does not satisfy no condition, there may be a blow up for some even for small initial data. Okay, so our question is, if we can we get pose some feedback law to this system stability or stable? So this is related to control theory. Okay, okay, we consider stabilizability of the following quasilinear Klein-Gordon-wave system with variable coefficients without no conditions, like this form. This is a system. One equation is a Klein-Gordon equation with variable coefficients. The second equation is a wave equation with variable coefficients. So this system can be seen as a Klein-Gordon wave equation system in curve space-time. So if we should choose a suitable metric, so we can reduce the Klein-Gordon wave system into the following form. Okay, of course, we cannot do without any condition on the conditions get some result, but we should need some conditions on the conditions. Okay, so you can from the equation you can see this is quasilinear term. This is also quasilinear term. F1, F2 is external force. It's related to feedback law. Okay, I will give the definition of the in the next page. Okay, here we should get some assumption on the conditions. Here, the time t belongs to this set. Okay, is bigger than 0. X is the whole space with n is a dimension bigger than 1. Okay, then where all the conditions are positive, and for any alpha, beta, gamma from 1 to n, okay, they is smooth, and the coefficients of the quasilinear term satisfies the following conditions. They are smooth supported in a bounded domain omega for any time t, and F1, F2 are two linear feedback control laws. Then we give the system uninitial data. We denote it 1.4. Okay. Okay. Moreover, we also need to assume the following conditions on the conditions. One seems complicated, but all this means that the conditions should be bounded and smooth And if we divide the derivatives of them will be small. Okay, this is the whole meaning of it. But we cannot control the degenerate case. Okay. 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 Let's see about system. If the feedback law F1, F2 is 0, and we assume the first coefficient is rho equals A, then the quasilinear system 1.1 to 1.2 admits a family of exactly time periodic solutions as the following form. Okay, it's because we consider the equation. The equation we found a special solution. If F1, F2 is 0, and rho equals this one, then we find the solution only depends on time, so we can get the time periodic solutions. Okay, as this form. This is special solutions, which are special solution of a linear system. This is a linear system of a quasilinear equation system. Okay. Furthermore, we saw that the linear equations admit the solutions UL and VL satisfy the small conditions, like this one, when corresponding initial data. Then we give the definition of a stabilization for quasilinear system 1.1 and 1.2 as following. The quasilinear Klein-Gordon-wave system 1.1, 1.2 is exponential stabilizable, provided that for any given initial data 1.4, one can find a linear feedback law, a control law, like this form, such that the quasilinear system admits a solution convergence exponentially to a solution of linear equation 1.11, where k and k bar type k are two linear operators. Okay, this is the definition. In our paper, we choose the feedback law as this form. As F1, F2 is like this form. So you can see this is like a Kelvin-Warwick damping term. Okay, the C and C type is smooth functions and supported in omega. This omega is same with the coefficients of quasilinear term. Supported. Yeah. Okay. You can we are some more exactly we C and C bar side C has this form. Moreover, we need is small in some derivatives higher. Thus, the quasi-linear system can be written as the following form. So this is a damped system, but C only supported in a subset of whole space. Other term on the whole space. So this is different of a classic damping term. Okay. According to assumption 1.5, we can write about a linear system this linear term can be written as the linear evolution system like this. Okay, A is an operator as this form, J1, J2, J3, J4 as this form. So this is seems some complicated, but it is but this system can get this evolution can this operator cannot generate a semigroup. So is a difference from classic linear system because the conditions depends on time t and x. If there is only on x, so this will be generate C0 semigroup. Okay. So if we let the conditions only depends on x, then they have this form. Then they maybe will be generates C0 semigroup. We can follow the following method, the papers method. Yeah. Okay. In general case, however, we develop the method of energy estimation. So since the linear evolution cannot get a semigroup, so how to get the global wavelength of linear system? So it's different from other papers previous. Okay, I will use the method of energy estimation to show the decay of a solution for linear can warrant a damping system in a suitable function space. Okay. Okay, here is the main result of I want to introduce. Let UL, VL be a small and smooth solution of 1.11. Yeah, that is the special solution of the linear system. Assume that the conditions satisfies 1.3 and to 1.50. Then the quasilinear Klein-Gordon-wave system 1.1 and to 1.2 is exponential stabilizable in the following sense. There exists a small positive parameter epsilon such that for any insulator which are supported in this set and satisfies the small conditions, then we can find a linear feedback law, control law F1, F2 satisfies that is Kelvin word damping. Then the collinear system, that is a damping system. That means the global solution is a small, almost is a Sobolev solution. Moreover, they have the following decay estimate. So, so in my opinion, in some sense, it's a scattering result for damping system. Okay. Okay. So if particularly if all the coefficients rho and a is equals to 1 and the other side other fish is 1, so the quasilinear Klein-Gordon-wave equation change is reduced to the following form. So our result also holds. So this is a Klein-Gordon operator. This wave linear wave operator. Okay. Okay. The idea proof. We sketch the idea. We write U and V as this form. UL, VL are special solution, special small solution, and it's small. W and Z denotes is like a perturbation to it's a perturbation term. In fact, okay, we substituting them into a damping system. We get the following perturbation system. Okay, it's a dissipative damping, dissipative perturbation system, Klein-Gordon wave system. Okay. The most difficult is how to deal with the quasilinear term. Okay, I give you the corresponding initial data where the conditions can be exact, can be computed exactly. Okay, this is for this is some external forces given this form, where we can see by another condition is by the small conditions. So from structure of system 1.18 and to 1.20, the quasilinear term may cause loss of derivatives in energy estimation. Thus, we have to introduce the smooth operator to smooth linearized system. Then a unique approximation solution can be constructed by suitable Nash model iteration scheme. Point out that the feedback law 1.15 is critical to derive the time decay property of solution for the linear coupled system. Okay, the smooth operator came from the work of the paper, the book of Alin Hack. Okay, we now introduce the iteration scheme. Assume that we have chosen initial smooth function W0 and Z0, and the size is not a solution of system original system. So there must be error terms denoted by big E0, 1E0, and big E20. We substitute this to original equation, we'll get that. Meanwhile, W0, Z0 should be chosen to make the error terms small and in some function space. In fact, in our case, it will be chosen in sublevels space. For here, the S is bigger than 0. Okay, then we'll iterated it step by step. The first approximation solution takes this form. Okay, this we have chosen. He has satisfied some condition. This is also chosen satisfies condition. What we found is H1 and tied H1. H1 and tied H1 is the solution of a linear varied damping system like this. For this idea, we can get the M's approximation step HM and tied HM by solving the linear system like this. The two linear systems have the same structure but with different conditions. Okay, but it is the same structure. So we solve one, another one is the same method. Okay. Thus, the M's approximation solution is of the form, get this form. Yeah. H1, HI, the tied HI is the solution of linear system. So the last step is prove this series is convergent. Series is convergent. So it's the whole idea of the proof. Okay, let's see how to get the global openness of the linear Kelvin variant damping Kelvin wave system. In this section, you can see the global openness for the linear damped wave system with variable conditions more precisely. For INAT and X belong to this space, let us consider the following system. It's a linear system, linear Klein-Gordon system is a linear wave system. F1, F2 is external force. It's related error term. Okay, we give about system a corresponding initial data and varnishing boundary condition. So we assume the conditions of the system is positive and satisfy following conditions. Yeah, so this condition is technical assumption. Okay, we require symmetric properties like this one and a small condition of the conditions like this. Then for NAI equals 1 to n, we choose two positive smooth bounded function phi, and type phi is a smooth, it's weighted function. This was following conditions. This condition is the technical conditions. Okay, and also this technical conditions and this technical conditions. All this condition is depends on we take the energy estimation. Okay. Let F1, F2 belongs to C1, this space. Assume that there is this positive constant C1 satisfies this following bounded conditions in Sobolev space. Then we have the following lemma. Some about condition holds, then the solution of linear coupled damped wave system satisfies the following decay estimation. Okay, you can see the decay. This is the decay law. Decay rate is this. Okay, how this is can be? It's not a difficult way. It's not difficult to get. We just multiplied by both sides of equation, linear equation. Both sides, the first equation by phi and u, and phi partial u. And summing up, and the same we deal with 2.2 equation. Okay, we can get by some inequalities, we can get the estimations or the energy decay. Okay, here I'll omit it. So we want to improve the regularity, so we derive HS estimate. HS is the Sobolev space. Okay, we introduce in order to keep the similar structure with system 2.1 and 2.2, we write it as a following form. Because this coefficient is bigger than 0, this is also bigger than 0, so we can divide it both sides by this. Okay. Why I do this? Because if we do not do this, we will add it. There will be a pair term we cannot estimate and cannot control. In fact, okay. Then we apply the operator to both sides of above system. We get this a new system where PS and the QS has the form, this form. It seems complicated, but it's all can be controlled by this form and this form. This good term, and this is good term. This is good term. Yeah, and this is also good term. This is also good term. Good term. Okay, and this can also get some good term to control the energy. Okay, by similar to lemma 2.1 method, we can get the following result. This is you can see it's also decay in time in exponent form. Okay. Okay. We have this now. We are ready to get the global openness for a linear system by fixed point iteration. First, we get the local solution. Then by decay of the system, linear system, we can extend the local solution to global solution. Okay, this is the global openness for the linear case. And it's decay, you can see. Okay, now we contrast the approximation solution. Since collinear terms may cause loss of derivatives, we introduce the family of smooth operators in smooth bounded domains. Let big Xa is smooth and is like this form. Yeah. Then we introduce the smooth operator as this form. This is follows from an hack, and also can see the paper of Klein-Gordon-wave they also introduced the smooth operator as this form. Okay, this second is a smooth operator on X. Then we get, sorry, I will quickly get it. Then we use the AMS approximation to first step to approximation estimate the solution. We get the linear system like this. With each step, we will solve this kind of linear equation. As we get the existence of linear, global existence of the first step of the existence. Forward this idea, we can get AMS solution of the system. Okay. Okay. The AMS approximation step will satisfy the following estimation. Okay. Finally, we get the time estimate like this. We can get this. We choose some parameters like this, then we get the proof of convergence. Okay, it's time. Oh, yeah, sorry. Okay. Okay, you can find you can prove the convergence. Oh, sorry. Yeah, happy birthday to Professor P.S. Professor Rescue. Yeah, thank you very much.
Thank you, Wei Ping. Are there comments or questions? Okay, if not, let's thank again Wei Ping, and I would like to thank all the speakers of this session for their very interesting contribution to the conference.